I welcome you all to this very first lesson of our branch of physical science, that is heat and thermodynamics. So, it being our very first class, we are introducing the first chapter of the branch of science, and that very first chapter is thermometry. So, I want us to know what thermometry is, what it has, the terminologies involved. We look at all the conceptual physics within the chapter, and then we connect to numerical problems. We see how best they are approached and solved. Then we end the thing, okay? So it's going to be a very clean class. Then after this, we shall see the next plan for the next lecture or a lesson, anything, okay? Now, as usual, I want you to give me a minute because I believe there are people who are having this as their first class at Science Scholars Academy. So you will give me a chance. Those who have overheard this, you will forgive me, but it's the protocol. We need to welcome our new members. They really need to know who are these people hosting these free classes, who are they, how can I really progress with them, things like that. So allow me a minute. I talk about the sponsors of this free class, and then maybe we can proceed. We have a look at the lesson targets, we check the syllabus book, we have a plan for the class, and then the plan for the next class, something like that. Hope I'm given the chance, okay? Now, as usual, the person talking to you is Dr. Paul, yeah? But you can just simply call me doctor, as most students always do. Simply doctor, that's enough, okay? So, have been sent by Science Scholars Academy to take through senior 6 and senior 5 students a topic of physics, and that is heat. Basically, thermometry for today. So they are the people who have sent me, and they are the sponsors, of course. Their vision, their mission, their aim, their goal is to create competent science scholars in Uganda. That means science is handled generally and also mathematics. By science, I told you it is biology, physics, chemistry, okay? Then the services provided are only three. Outside the three, that is none of their business. Holiday coaching, that is compulsory to all science students of the country. And I told you this one just goes for 100,000 for your whole combination plus ICT and GP. You study and of course pass. Those who have been with us at least can tell and be evident of this. The homeschooling program, this is for strictly and strictly students who don't have fees, because you study for the whole term for as low as you can pay. And then also those with health issues that may not allow them to be at school, and also some other issues. Then also the day scholars who really want to come back from school and revise at night. When chest fees, they stay locked in. Things like that. When they come around on weekend, they also connect academically. They're also part of the homeschooling program. These sessions of consultation, advice, and counseling, those are free of charge. Okay? No one will charge you for that. So we just give back to the country. So you all know what we do, video classes. That is the major thing. And as of now, we are concentrating on the four major science subjects, okay? If it's a live class like this very one, it's via Zoom. If you miss it, we record it and store it on our app. But we usually use the Google Drive because it's the one that is more student friendly than our application, okay? Then the other thing are the notes, sample papers, scoring guides, but those ones we already just provide them for free. Many of you have requested for notes, but we don't sell them. We just use them for classes like this physics book A with the extracted topic of thermodynamics and heat. So we are just going to use these very good notes for the class. They are not sold, but they are provided to you. That's if you become part of what? Premium. For those who have been requesting, okay? These are the things you can just read through and can just take a screenshot, read through later. And so we concentrate on only and only science students of A level, okay? The other subsidiaries are also handled. Whichever classes we've been holding since 2015, they are available. But we just refine them and filter them to come out with the best and they are always accessible throughout the year 24/7, even if you need them at midnight. This is our contact. Always just try to reach through and you'll be helped, okay? Then you can check our YouTube channel for the free sample classes. Those who may want to look at more of the topics, visit the channel Science Scholars Academy and enjoy. Any social media platform, it can help, but basically YouTube for the classes. So thank you for that chance to talk about our sponsors for the free class. So straight away, don't worry, these are physics textbooks. This is called Neocon and Parker. This is called Roger Moncaster. There is also Tom Duncan. I've not carried it because I want to give you some research from it. With the very first task being looking for the book. Okay. Now, we are going to first go through the syllabus. We see what they want. Then we introduce the topic here. Then after we start going through our notes. And then we see what we have for the day, what we shall have for the next class. And yeah, so thank you for coming. Now, topic 9. So when you look at topic 8, someone may be like, why topic 9? Why not topic 8? Topic 8 is mechanical properties of matter. We shall cover that in holiday. Yeah. So for now, topic 9, heat and thermodynamics, where the very first topic is thermometry. So if you look critically, it's only 2 things they need, because now topic 10 shall be heat quantities, and that is the next thing we shall be covering. Hope the screen is clear. So we are only and only concentrating on what? On the thermometry part. So what do these people want us to know? In line with what they will set for us in the end. So they want you to be in position. I told you these things you see in blue, they are like the competences, okay? So these are things you're supposed to achieve. Those of you who keep on asking me for scenarios, I will provide them. But make sure before you ask for scenarios of thermometry, ask yourself, can I do the blue things in tutor's student-friendly syllabus book? Can you relate the expressions of temperature scales? Can you relate them to solve real-life problems? Of course, you're going to first handle the computed tasks before you delve into a scenario, but I'll tell you all that, as I've already told you. Then after that, before you ask for scenarios, ask yourself, what do they consider when setting a scenario of thermometry? They look at, does a student, or can a student really relate expressions of temperature scales? And can they use those relationships to really solve real life problems? Then they ask themselves again, can these students compare the different types of thermometers and how they are used in real life? And that is your task. You're taking it, you like it or not. Why? It's having project work. Some of you are not really sure of which project work you're supposed to do. So you need to concentrate till the end. Understand what you need to know under the topic. Which project work are you doing under the topic? Okay? Now, under the very first competency that is supposed to be achieved, they want us to be in position to review the terms and concepts. Things like thermometric properties, fixed points, and different temperatures, okay? We are going to see that. They want us to derive. Please note, they want us to derive, not doing anything else, but to derive expressions for the different temperature scales, and we are doing that today. Even this thing of reviewing whatsoever terminologies, it's going to be done today, okay? And we are going to solve numerical problems still when? Today. So this part of comparison in daily life, I've told you that for years I've been usually giving that to students. And I'm going to tell you the best way you can really make research on it and really make notes and be organized. I always like it when you make your own notes from your own research for certain concepts that are really student friendly, because you really remember them forever. It's not that everything the teacher is supposed to be giving, you know. For the new curriculum, some of the things are supposed to be student-centered, and we shall always practice that every time we meet. Hope I'm communicating. So these are the things. So the first competence is mine, and we are dusting it today. Then the next is yours. So our next stop shall be heat quantities, topic 10. So we are completing topic 9 together. We shall have time in the future for presentations. For those who will have some good work, you come here, you present your work, you explain, I give you scores, I upload the video, and you're watched nationally. Okay, so that is it. So the lesson target is going to be very simple, and it's only one. Okay, so I'm going to say lesson target. Yeah, these days I don't want to write lesson targets um, because they are always so many. But if I expose the book has the targets. So if I say that we are dusting thermometry, I mean that whatever you're seeing on the screen under thermometry topic 9 is supposed to be covered today. And the next stop shall be what? Heat quantities. So very fast, the lesson targets. We are supposed to dust thermometry, completing it. Then after, I'm supposed to leave assignment, stroke research, or even both. You all know there are classes where I only leave research. There are those where I only leave assignment. There are those like this one where I leave both. So you just need to be ready. And once those are given, we have our next stop. Okay? And that is it. And that is it. Now, the topic is thermometry. Sorry for those who have been waiting for me to start, but you always need to be patient because I told you this is an academy. We are supposed to give things time, cover them for once and for all, okay? So the topic is thermometry. Before you even look at what are those things really under it, I even made an error by reading through whatsoever is below it. We had to first understand what is the thermometry all about, okay? Now, these are our notes. Thermometry, as we hear the word, it is to do with thermometers. At least first appreciate that. Most of you have heard it everywhere. You've heard of words like trigonometry. You've heard things like geometry. So you've heard the word metry so much. The word metry is to do with measurement, period. Measurement. You've had geometry, you've had trigonometry, you've had a lot of things in that line of metry. So when you see metry, think of what? Measurements. That is one. So of course, this is a science, because why not? It's the things we are supposed to cover at the academy. What does it deal with? It deals with, they are saying, I even fear to use the word temperature because it will again be an unfamiliar term, but I have no choice. So thermometry, first and foremost, it is a science because it is under physics. And physics, you all know it is science. We deal with measurement of temperature using instruments called thermometers. What are we really measuring? We are measuring temperature of a body. You people, when they say a body, what do they mean? Okay, is a car a body? Or the body is strictly this body of ours that has the head, the chest, the abdomen, and so on? You tell me. What is the body? Okay, is a car a body? Or the body is this one with the head, neck, thorax, abdomen? You tell me in the chat as we proceed, because I really need to be knowing which people, okay? Yes, it is. I only need one answer. Thank you, Jotham. So even a car is a body. The only writing that connects to us is the human body. So when they say human body, it is strictly human. But when they say body in physics, even a cup is a body. A car is a body, a ladder is a body. Okay? So the temperature of anything. So that is the thermometry you're handling today. So when you see me measuring temperatures, don't be surprised. Understand, it is the science that really sends us to that. Which instruments are we using here? Thermometers. Just like the way the science sounds, thermometry, that is done. So we are seeing two things that are unclear here. or what you'll be calling the unfamiliar terms at higher levels of education. We are seeing thermometers and temperature. The rest are okay. So that means you really need to know what is this temperature thing and what are these thermometers. Yeah, these introductions are very key. They help you to understand things that really give you a time in the future. Because now, as far as a thermometer is concerned, I just want to let you know that a thermometer is just always having a scale on it. That is the only thing I want you to learn as of now. You understand? That's why they are telling you at this point that the temperature is measured using a thermometer which has a scale on it. So just understand the thermometer, yes, it measures temperature. What is so special with it or on it? It has a scale. Then later on, we are going to split that scale and see what is this scale. Okay? Then what is temperature? First, appreciate as a science student that temperature is a number, not anything else. So for you to come out and tell us that this is a temperature, it shouldn't be a letter, it should be a number. And it should show us, it should express how hot or how cold the body is. Are we together? Most of you know what I mean by hot and cold. All of you, that is English. So that number that really tells us that, this body is hot. That number that tells us, this body is cold. So that number is what they call what? Temperature. Because it is expressing how hot or how cold the body is. And they are saying on a given scale. On a given scale, simply because we are measuring it using a thermometer that has a scale on it. Scales are the first things that give people a time in this topic. So you need to listen well. Okay? Or you can just define it. Why I'm not giving the definitions time? In competence-based assessment, you're not supposed to define anything, but you need to have understood the definitions for you to apply whatsoever you're supposed to apply. So never be stressed about how something is defined. That is cram work. It usually caused cram work in the old curriculum. Someone wants to cram how the definition of temperature is said as it is in books. But just understand, it is a number, expresses or shows how cold, how hot. Okay, that is enough. They use a thermometer, it has a scale, just that. Then be ready for the scenario. Okay. Now, the very most important thing that you're going to learn today, something that is always not so clear in O level, and it is going to really dominate today's class, is what they call a thermometric property. Okay? When you hear something like thermometric property, if they tell you that, if they tell you anything like a property, it is something you really need for you to be called that. Okay? You understand? Properties, look at them as requirements. That for you to be in school, there are things you need. You need a book, you need a pen. So when they talk of a property of a thermometer, it's its requirement. It really needs it for it to do what it's supposed to do. So for these thermometers to really measure the temperature, we are saying it really needs a property that is called the thermometric what? Property. I want you to listen carefully. You see, these thermometers are very weird, and you're all going to be surprised. Some of you have not heard of this topic and are hearing it for the first time. You really need to give this point of thermometric property time. So when you hear property, it's like a requirement. The thermometers really need it for them to claim that, or for them to be in position to measure the temperature. We really need them to do what? To measure. Now, properties are either physical or chemical. You even know that from chemistry. So the property cannot be a chemical one. So as you're defining it or as you're thinking about it, never leave out the physical part. So the property is a physical one. Okay? It can't be chemical. There are two, chemical and physical. So this can't be chemical, it is physical. Now, there is someone may be like, okay, we've heard of the temperature, we've heard of the thermometers, we've heard of everything. But then the topic is heat and thermodynamics. Where is the heat coming in? Where is the thermodynamics coming in? So thermodynamics, we shall see that later on. It's a specific chapter and it is the last one in the topic. But for now, it is strictly heat. So when they say heat, remember we have talked of how cold and how hot. So we can have a hot region and we can have a cold region, okay? Look at you trying to iron something. When you iron something, it's becoming hot. But what has been hot is this flat iron. Eh? Of course, it has that hot plate. But then in the end, the cloth also becomes hot. But remember, the cloth was cold. I don't know whether you're getting the scenario. So we are looking at the hot plate of the flat iron making the cloth hot. So we've had transfer of a certain form of energy from a region that is hot, that is the plate of the flat iron, to a region that is cold, that is your cloth. So that energy you're transferring from the hotter to the colder region is what they call heat, period. And you all know that we have three subtopics. You will forgive me, I've not given you the breakdown of the topic, but it is cheap. The first one is thermometry. The next chapter is calorimetry, where we talk about heat quantities. Then the third one is called heat transfers, where we shall talk about the different ways, processes, and whatsoever modes through which heat is transferred. We have conduction, we have convection, we have radiation, okay? So those are the different ways through which heat can be what? Transferred. So without going deep into that, just understand that it can be what? Transferred, period. But how is it moving? It is moving from a region where it is too hot to a region where it is too cold. So the energy you're transferring is what they call heat. So hope you see the connection between temperature and heat. Temperature is just a number that shows us how hot, how cold. Heat is that energy that moves from somewhere hot to somewhere cold, period. So that is a top-notch introduction to the topic thermometry. So by now you should be a prophet and you should be in position to tell whatsoever I'm going to find in the future. And I will not repeat whatever I've said. So what hope you're taking note. As I always told you, always have a side notebook. Whatever is not on screen and I say it, you note so that you stay on track. That's why I try to keep the pace as moderate as what? As possible. So let's look at those terminologies that we are going to meet in the topic so that we don't find our time with it. Because I don't want us to pull ropes with the very first chapter in a topic. Why would we? Okay. Now, the very first definition or term is thermometric property. One thing I really urged you to understand is that it is a physical what? Property. In whatever you're planning to forget, never forget that. Very key. Very key. Physical property. Now, remember, I've told you, okay, let me first tell you the secret that people do not know, or that people, or that they will never tell you, or something that you knew, but you had never given it time. I don't know. Are you people aware that a thermometer has never measured temperature? Like they never measure temperature directly. Have you ever thought of that? You people, they just get a thermometer. A medical doctor just gets a thermometer and puts it under your armpit. And then for you think it's temperature being measured. It is really something different. And it's what we are going to talk about now. So it is some bit of secret that some of you have never thought about, but you really need to appreciate it today. The thermometers never measure. They never measure. They never measure temperature directly. So very fast, let me write it. The thermometers, I'll put this in capital letters, never measure temperature directly. That's why you're going to be shocked that in most of the calculations will be asking us to measure temperature. Yeah, because we are not in position to. It never happens directly. So someone may be like, how does it really happen? So don't look at thermometers as weighing scales. Weighing scales, you get your anything you're weighing, you put it on the weighing scale, you read the figure directly. That does not happen with thermometers. It cannot just happen like that. There are some behind the scenes you really don't know. Someone may be like, but I just see the value. Yes, you see the value, but there is something that they hide, and it is that something that you're supposed to learn today. Okay, so how is this done? I'm going to give you one example of a thermometer that you guys know, and you're going to be shocked. You're going to be shocked. Have you looked at these thermometers, the ones used in O level? Because all of you did chemistry at O level, and you know those thermometers, whereby when you put it in something hot, it has it has a red thread that tries to that tries to okay, whose length tries to increase, or that thread that tries to rise when you put it in something hot. Have you looked at those thermometers before? I don't know. Have you looked at those thermometers before? Before I even before I even explain to you what a thermometric property is, I want to first give you a case scenario that you've seen before. Then maybe we can connect to the content later. You see, you're supposed to connect these things to daily life so that even attempt of scenarios is easy for you. It's not like in the old curriculum where we could just come here and explain the content, make you cram it so that you can pass those weird papers. Now you reach an exam, you're supposed to apply. So you tell me, do you guys have any past history of such thermometers? Have you looked at them? Someone is like, yes, we even used them at UNEB. I don't know whether it's the same for my people. I will not say that. But let me try to show you something small. The problem you people don't want to embrace. People don't want to embrace the internet. But I'm going to show you something small here. Let me put in liquid in glass. Okay, today one of the things we are going to look at is a certain thermometer they call the liquid in glass thermometer. So let's see here. I don't know if you can see the screen. Okay, let me put in liquid in glass. So all of you agree that that thing is like a liquid because it is in position to move, and the thermometer you were using was glass, because I believe some of you broke those thermometers even. So that is clear evidence that it was glass. And inside we had a liquid which was trying to rise. So that's why I'm saying liquid in glass thermometer. So let's look for its animation. I remember telling you that if at all you're having classes with me, you're supposed to have the Pinterest app. The Pinterest app tries to show you those images. So I want to request all of you now, go to Pinterest. I told you to get the app. Type in liquid in gas thermometer. Try to look at it so that as I say certain things, you really know what I'm talking about. Okay? Um, let's see this. So you keep quiet and listen. Okay?
In this video, we will deal with the design and operation of a liquid in glass thermometer.
It's what you use. It may look somehow different, but it's what you use. So for you, just try to listen. Just, just try to listen, okay? Hope the English is going to be clear enough. So there are just 3 minutes, listen. So every time you find something as you're reading, especially to the senior fives, because now for you have a lot of time. If you have that kind of behavior and maintain it up to senior six, you're going to pass. You find something confusing, first go to YouTube, go to Google, go to Pinterest, first get some images. You see, with images, education becomes so easy because you understand things more than you would when you just use plain notes, okay? So, assuming I was also a student, I came across liquid in glass thermometer, but I really want to look at it. I would also come here, put in, I see 3 minutes are not many. They cannot really cost my future. I watch. If I get anything, well and good. If I don't, I look for another video. Okay? So you really need to be persistent as you study. In the end, it will finally work out. Okay? So we go.
In this video, we will deal with the design and operation of a liquid in-glass thermometer. So let's get started. Liquid in-glass thermometers are based on the principle of thermal expansion of substances when they are heated.
You people, have you heard that for us, we want the thermometer to give us the temperature, well and good period. But have you heard what that guy has said? I'm trying to be now like a VJ because I know I have my people here who find issues with English of these people. He has said that these thermometers depend on thermal expansivity. Oh, they are okay. He has said thermal expansion when those substances are heated. Have you heard? So you learn it from me today that thing you see rising, it is a certain substance and it is expanding. That's why you're seeing it going up. So don't think it is temperature moving. That's what most people think. Trust me. Trust me, that's what most people think. But that's not it. Uh, what you're seeing rising is a certain substance. And when you heat it, we expect it to expand. And when it expands, that's why it tries to raise. It tries to raise. Then when you put it in something cold, we expect it to contract. That's why it goes down. Are we together? So it's not temperature moving. So thermometers can never give you temperature directly as you may think. But there are always things that happen behind your back. And they are the things you're supposed to understand today. Okay? We go.
A liquid in a glass tube, also called a capillary tube, expands when heated and contracts when cooled.
Have you heard that we are having our car tube? They have called a glass tube. They have called it a capillary tube. And that substance inside, when heated, it expands. When cooled, it contracts. But me, I'm going to make it better and say, when heated, it expands. Hence, it rises because that's what you see. Then when cooled, it contracts. Hence, the level falls or it falls. But remember, it is a certain substance inside that capillary what? Capillary tube. I want you to understand that. Then we connect it to what I'm supposed to teach. Okay? We go.
A calibrated scale can then be used to read off the respective temperature that led to the corresponding thermal expansion.
Have you heard that now this scale or whatever we are using is calibrated, but the values we are seeing there are values of temperature? I want you to listen. And that value of temperature is simply a temperature that has led to that length. Do you understand? So don't expect to get a thermometer, put it in something hot to just give you the temperature directly. No. That something hot is responsible for heating that substance in that capillary tube. Then the substance is supposed to expand and rise up to a certain length. So where it stops, it will show you a corresponding temperature, but this temperature is simply corresponding to a length. Okay? Now it is simply communicating that it is this temperature that led to my increase up to this point. Do you understand? It's not that the temperature that shows itself that, yeah, I'm here. No. The hot thing into which you have dipped the thermometer is supposed to hit the substance or the liquid in the capillary tube. The liquid is supposed to expand and rise up to a certain point. That point will have a corresponding temperature. So it is now communicating that it is this temperature that has made me to expand and rise up to this point where I am. Okay? But in actual sense, first we are seeing a column of a liquid that is increasing. First, we are simply seeing a column of a liquid, but it has a corresponding temperature. So understand something like that. But we are going to connect it to the notes and proceed. And then calculate. Actually, everyone is going to be in position to calculate. Calculations are easy if you get the concept. Just need to do around 2, 3, 4, 5. Okay, but let's dive too much into the literature and get the points. Okay, we go.
Such thermometers are also called capillary thermometers. The liquids used in such thermometers must have certain properties in order to be suitable for use. For example,
Have you heard? They have said that since this liquid is moving through a capillary tube, don't get surprised when in a scenario they call it a capillary thermometer instead of a liquid in glass. Then they are saying for you to use that liquid in that thermometer, it should have certain properties that are really going to make it suitable for it to be there. For example, you all see the color of that liquid. It is somehow gray silver, something like that. So that color, you can really see it, okay? So first and foremost, it should be opaque. By opaque, you can see it. Because if it were transparent, we couldn't even tell. That's why water is not so good. Because water is transparent. But these other liquids that are somehow colored are okay. Because they can enable us to see the increase. That's why as a student, they give you a liquid that is red. Okay? So that it is opaque enough for you to read off things accurately. So that's one of the properties. But the properties are too many. The liquid should not wet the glass or the capillary tube. It's going to bring issues. A lot of issues come with the wetting. If you know adhesion and cohesion forces as a physics student, you know what I mean. So we should avoid wetting the glass at all costs. What we are using should be what? Opaque, so that we can clearly see things. And so many properties, we are going to read them. And you're also going to hear some of them just immediately I replay this video. Now you listen to those properties that are really supposed to be exhibited by that substance we are going to use in the glass. Okay, we go.
they must not freeze at low temperatures, which is why water, for example, is not suitable. The liquid should also have a sufficiently high boiling point so that they do not vaporize at high temperatures. Furthermore, the liquid must expand evenly with the temperature in the measuring range used. Otherwise, an uneven division of the scale on the thermometer would be necessary. Also, for this reason, water is not suitable, since water expands unevenly due to the density anomaly.
You people, have you heard what they have said? That the liquid you're using, it should not just freeze anyhow. Because if the temperatures are low, we expect things to freeze. So the substance we are using should not have that excitement of easily getting frozen when the temperatures become low. It should be kind of endurant. It should endure. Even when the temperatures get too high. Are you listening? It should not just start forming vapor straight away like water. It should first try to endure those very high temperatures. Otherwise, we may not use the thermometer in maybe the Swiss Alps that are so cold, or even in the deserts that are so hot. Yet we need to use them there. So the substance we are using, the liquid we are using, should not have that excitement of easily getting frozen and easily vaporizing. Easily getting frozen at very low temperatures and easily vaporizing at very high temperatures. Then its expansion should be even, or it should be uniform, because you're increasing your temperature slowly. So we expect something to also, or that substance or that liquid to also be expanding slowly. I cannot increase my temperature by 1 and then you expand over a very big length. That is not fair. And they are telling you that's why water cannot work here, because there is what they call the abnormal expansion of water. We even study it in phase equilibria in chemistry. That is equilibria 2. Water has an abnormal expansion and it owes that property to the density. Okay? But we shall learn all that. But hope you're getting something at least. Okay? So we proceed, I think.
However, liquids which have all the required properties and are therefore suitable for use in liquid in-glass thermometers are also referred to as thermometric liquids. In the past, the highly toxic mercury was used, which has a solidification temperature of -39 degrees Celsius and a boiling temperature of 357 degrees Celsius. Nowadays, usually blue or red colored ethanol alcohol, with a melting point of minus 115 degrees Celsius and a boiling point of 78 degrees Celsius, is used instead of mercury. In this temperature range,
Have you heard what they have said? That long ago they used to use mercury, but it was highly toxic, so they had to do some changes. But why the mercury was really wanted, it had a boiling point that was very high. You've heard it was in 300. That means it could sustain all the 200s without what? Vaporizing. Then its freezing point was in negatives. That means it could withstand all those negative temperatures without it getting any problem, okay? Without it freezing. I think that was very clear. But nowadays they chose some form of ethanol that is either blue or red. I think you've had that. And I think now we can proceed. So at least you have now appreciated that water never works or it's not good, but mercury and ethanol, alcohol, are actually good. And these substances or these liquids we are using inside the capillary tube, inside the glass, inside the thermometer, they are also called thermometric what? Liquids. Are we together? We go.
everyday temperatures in the range between minus 20 degrees Celsius and plus 50 degrees Celsius can be well covered. The measuring sensitivity of liquid in glass thermometers increases with the amount of liquid in the thermometer. The more liquid there is, the more liquid will expand and rise in the glass tube. For this reason, liquid thermometers have a reservoir to increase the amount of liquid in the thermometer. Too much liquid, however, would cause the thermometer to react very slow to temperature changes, as the heating of the liquid will take longer and the liquid will take longer to adapt to the outside temperatures to be displayed.
Have you heard what they have said? That why they chose this ethanol, its temperature range is so good that it covers the normal temperatures of the environment and most experiments in physics and chemistry of negative 20 to 50 something, okay? So that means the ethanol is very okay. But then they have said, we have a reservoir, that bulb you're seeing down. Let me just call it a reservoir, not a bulb. So it's the one where the liquid is kept. And they have said the more it is, the more it can expand, and maybe the higher we can rise. But they have said it being too much is not so good. You understand? That if something is too good, if something is too much, heating it is now going to become a problem. That it's going to really take longer for it to respond to those temperatures and really adapt to the environmental ones. So yes, when it is too much, it expands and we can go higher. But again, it being too much is not good. That it's really hard for it to be heated. You understand? Expansion is even going to become harder, things like that. And have it in mind, we are remaining with only 30 seconds and the video gets done. Hope you have been trying to take some important notes. Don't just look on. Okay? So we go.
Thus, the reservoir should not be too large, but also not too small. Why did people actually use toxic mercury as a thermometric liquid in the past? This was not only because of the wide temperature range of theoretically minus 39 degrees Celsius to 357 degrees Celsius that could be covered with it, but also because mercury hardly wets the glass tube. The capillarity is therefore lower and the temperature can be displayed and read off more accurately. Especially in the scientific field, this used to play an important role in keeping measurement uncertainties as low as possible when measuring temperature. We hope you enjoyed the video and found it helpful.
I think you people have heard. So I'm giving you a task of you going and watch other videos on other what? You can just look at the name of the YouTube channel and realize maybe this person has good videos. Then you also go and check. You just take a screenshot. So they have said that according to what I recently explained, so the reservoir should not be too big and it shouldn't be too small. It should just be enough, okay? Then they have said why they chose mercury those days. It's that it used not to wet the glass, but this ethanol is actually strongly wetting the glass. But it also has its advantages over the mercury. The mercury was too toxic. This one is non-toxic, but it wets the glass, but they have nothing to do, okay? So hope you've liked the video and you've gotten something from it. So the thermometers never measure the temperatures directly. But there are certain properties they have that connect to the temperature, period. So I think we can now go back. Let's go back. So I had said, hope we are back to the screen and all of you can see it. So we had said that thermometers never measure temperature directly. Okay? They use properties. They use properties which change as temperature changes. That is the simple secret, nothing else. For them, they have their own properties. These properties change as you change the temperature. You get the liquid in glass thermometer, dip it in hot water, it expands and it rises so high. You now put it in ice, it now falls and goes down. You get? But remember, this is a liquid trying to expand and it is increasing the liquid column. So that thing is called a liquid column, yeah? That thing inside the capillary tube. Hope you all know it is a liquid column. So when you see it somewhere, don't be surprised. Now, these properties they are using, they are the ones they call thermometric properties. Hope you've learned that. So those properties they use, they are the ones they call thermometric properties. Is it okay? Now, the other thing you really need to understand is the change. You get? The change we are talking about has two factors that you shouldn't forget. You people realized that as temperature increases, even the liquid rises more. You increase the temperature more, you understand the column rises more. You increase more, it rises more. You make the temperature fall, even the column falls. You make the temperature fall the more, even the column falls the more. So that form of change is what they call linear. I don't know whether you guys know that. We even talked about this in coordinate geometry when we are teaching straight lines. That when you see something linear, if they tell you something is changing linearly, that means as the other one is changing, it also changes. Hope we are together, eh? If I say x changes linearly with y, as x changes, okay, as x increases, y increases. As x decreases, y decreases. That's what it means. Then there is something you really need to understand that you people, you just look at the liquid in glass. It's the one I really like so much because it connects to the science very well. When you see that liquid increasing, it increases continuously as a liquid. It does not increase, then stop, increase later, or it does not leave any breaks. It just increases as a continuous column. You understand? So even the change, have it in mind, it's continuous. You can never find breaks. No. Breaks can never happen in the change of the thermometric property. So as you change the temperature, yes, even the thermometric property is changing, but have it in mind, it's linear. Then also it is continuous. Also note that. So every time they tell you about a thermometric property, there are things you're not supposed to take lightly. The continuous change and the linear change. Put them together. Then you also recall that these thermometric properties are physical ones. I also explained that. Okay? Now we are going to read the definition and I expect you all to make sense out of it. Then we are going to also look at other thermometers because it's not only the liquid in glass, there are so many others. So you're going to look at them in the notes so that you have a reference of which videos you're going to watch and make notes out of them and keep your work. If you do like that for 1 year, that is senior 5, you will have the whole of next year to just revise this work and perfect, get good points and proceed. I told Form 6s these things last year. I don't know if those who applied are going to pass. Okay? Now, We go back. What are they saying here? So the very first terminology I told you, it's a thermometric property. So we first looked at one, then we connected to other things. Yeah, we connected to other things. They are saying a thermometric property is first and foremost a physical property, that one we know, which varies linearly, I've explained that, continuously, I've explained that, with temperature. So thermometers never measure temperature directly, but they use some other properties, which we are sure that as you change temperature, they're also going to change. So they will communicate to us the corresponding temperatures, then we shall measure, period. We go. What are the qualities of a good thermometric property? Students usually failed this in the old curriculum. They don't understand thermometric property and thermometric liquid. Thermometric property is general. Thermometric liquid is strictly under the liquid in glass thermometer. And that is all. Okay? The very first one is from the definition that the variation should be linear and continuous with temperature. Period. They are saying it should vary over a wide range of temperature. Do you remember the other thing? There is a way it connects to the normal properties we have been talking about. That the range should be wide enough. It's somehow connected to what we said, that at very low temperatures, the liquid we are using in the liquid in glass thermometer should not freeze easily when the temperatures get too low, and should not vaporize easily when temperatures get what? Get high. That it should be very stable over a wide range of temperatures. Too low, it is sober. Too high, it is sober. What you guys these days call, I think, gumite. I don't know what it means, but I think it's connected to that. Very low temperatures, gumite. Very high temperatures, gumite. It is there. So that is also very important. It should correspond to a unique or single value of temperature. We are going to see this slowly. Hey, that's why some of the liquids we have been using, like mercury, ethanol, water, the ones we have been talking about, you all know they have those specific melting and boiling points. You understand? So that means they are so special at a certain temperature. So this shouldn't be really a surprise. You should just understand that when a unique value, single value of temperature comes in, the thermometric property should be in position to behave in one way or the other. But we are going to see this as we proceed. It should respond to small unit temperatures, like it should be very sensitive. You understand? That's why, even if you just get that car thermometer and just put it on top of boiling water, that steam that is coming out, you've not put this thermometer in hot water, but you're just looking at the steam. Even if the water has not yet started boiling, maybe it is somewhere at 40, and you just place the thermometer on top without dipping it, you will see somehow the column rising. You understand? Simply because that small change in temperature has been appreciated. Okay? That's what we call sensitivity, that it is too sensitive, that even a slight change in temperature is noticed. So that is so important, and it is good of any thermometric property in place. Do you try to understand? Yeah. So it will somehow connect to the qualities of a thermometric liquid, but the language is supposed to change. But if at all you've been attending, the moment you go into the literature of this content, everything will be kawa, and you understand the work. Okay? Now, let's look at the types of thermometers and their thermometric properties. Now, here I want you to listen critically, because we agreed that I'm doing this first part that has numerical problems. The other part of how those thermometers are used in daily life, it is your research work. After all, it doesn't have calculations. Its calculations are actually covered in this class, so it is some sort of working together, okay? Now, there are so many thermometers. Let me first list them so that as you're also reading, hope people are taking notes and taking screenshots slowly. You have a tendency of stressing me with notes after classes. Take screenshots if at all you're attending, or you wait for the end. We take screenshots together slowly. Is it okay? The first one is called the liquid in glass thermometer, which we have looked at on YouTube. And I've told you why it's called like that. There is a thermometer they call the thermocouple. We shall look at it. There are thermometers they call the resistance thermometers. Now, these resistance thermometers, you all know resistance is to do with electricity. Electricity, when you hear of electricity, you think of an electric wire. Have I lied? I've not. So we use wires here. And you know wires are made of metal, excuse me. And we have so many metals. But the best metal here is platinum. So you really need to know why is really platinum chosen in all metals. So that's why the thermometer may now be specifically called the platinum resistance thermometer. You understand? Trying to notify that the electric wire in place is that of made of platinum. We have what they call the constant volume gas thermometer. We have what we call the constant pressure gas thermometer. Then lastly, we have what they call the pyrometer. Yeah, it got a lot picky when it came to the new curriculum, and we are going to see that. Yeah, I'll talk about it at the end so that you don't mess up. Yeah? But if at all some of you have ADHD, this is what I mean. So as you're making your research, leave out the total radiation pyrometer and maybe look at the optical one. We shall see that because your curriculum said that we shouldn't consider it. But if at all you're there and you're this student who really wants to do radiography, I'm talking to the PCB students, you should know it. You need that knowledge. Why would you leave out anything to do with radiations as someone who wants to progress and do radiography? That is very bad. Yeah? And we need to advise you as you learn these things so that you know the impact of all your steps and decisions you're taking. Okay? Now, those are the thermometers that we are going to look at or that we need at your level. Now, what are those thermometric properties? So we all know that these thermometers cannot just measure temperature just like that. What do? For them, they have their own properties, which properties change as temperature changes. So what we get is a value of the property, but this value of the property corresponds to the temperature that is making that cause. Are we together? That you've gotten a thermometer, a liquid in glass, you've dipped it in hot water. It's not reading the temperature, no. For the liquid inside, it's going to expand and the column will rise. So it is just rising because of expanding, because of the heat. But it's in the end going to give you a temperature that might have caused that extent of rising. I hope you understand. Because none of you is asking me questions, so I believe that point is now clear. Now we start. What are the thermometric properties for each? So for the liquid in glass that we have looked at, the property that changes when you dip it in hot water will be the length of the liquid column. Have I lied? I have not. I believe that is very clear. Thermocouple. Which property of the thermocouple is going to change when you dip the thermocouple in ice? What is going to change is the EMF. EMF is voltage. Your physics students, your engineers, I believe you know that. EMF is measured in voltage, or what you call volts, okay? That means that this thermocouple has a certain instrument or device that measures voltage. That means the moment you dip a thermocouple in ice, you've caused a temperature difference. Now, the temperature difference you've caused is going to in turn cause a voltage difference, or it's going to cause current to flow, things like that. I don't know whether you people are trying to understand. So the change in temperature just makes the voltimeter of the thermocouple to register a change in voltage. So that change in voltage, it likes it or not, it's supposed to give us a corresponding change in temperature. Then we record the temperature. Do you understand? Yes. Platinum resistance thermometer. What does it have? It's having a thin wire. I told you that. We expect this thin wire to conduct electricity. Who doesn't know that metals conduct electricity and platinum is a metal? So when electricity is conducted, you all know that electricity is either conducted by free mobile electrons for solids like metals or by free mobile ions for liquids and aqueous solutions. Are we together? So we expect this wire to conduct electricity. Who is going to conduct? It's the free mobile electrons because the wire is solid. These electrons, we expect them to move. We are saying free mobile. They are supposed to move. As they are moving in physics, motion must experience resistance for the science to become beautiful. Why would motion be free? After all, even as something is falling, we put gravity there and see gravity is doing something. When you push it up, we say it is against gravity. When something is moving on a rough surface, we say there is friction. We are bringing all that to just make things fun. So as these electrons are moving, we expect them to experience some resistance to their motion. But remember, they are conducting electricity. That means you are resisting electricity to be conducted. Okay? So that means you like it or not, electrical resistance must come in. So if it is a platinum resistance thermometer, the moment you dip it in ice or dip it in hot water, what is going to happen? Some resistance is going to be what? Noticed. Someone is like, but where are you going to get the resistance? This thermometer has a device that measures it. Remember, resistance is measured in ohms. Have you heard of the ohmmeter? You can search, you go to Pinterest. This is the name of the app, yeah? Because I want to be saying certain things as you really connect to them all. This is the name of the app. It has very good images. Some are original, some are AI generated, but get the app. So that when I say things like ohmmeter and you've not heard of it, you go and search. How does it look like? So this platinum resistance thermometer may have that device that can measure resistance. So when you dip it in the hot water, for us, we only expect one thing: electricity is supposed to be what conducted. But the free mobile electrons to do it must experience resistance. So for us, we are just looking for that change in resistance. It is what that will give us a corresponding change in temperature. I think we are together there. I think that is obvious. I don't want to go into deep details how resistance is connected to temperature, for you just understand. The moment a change in temperature is noticed, how? You get your thermometer from a table, put it in hot water. That is already a change in temperature. It may not read it directly, but it is a resistance thermometer with a ohmmeter. It can measure the resistance of the electrical wire, which is within the thermometer. So that change in resistance, or the resistance that is going to be measured, shall give us a corresponding thermometer that has caused that change. Okay, so in this place, the resistance is the property that is changing as temperature is changing. Don't forget the change is linear and continuous. You get? Yeah, we must produce serious engineers, so you should not cram anything. You should become very good contractors that are competent. Hey, so you should understand each and everything. What usually confuses people is that this one is called constant volume thermometer, but again, it is pressure that is the property. This one is constant pressure, but again, it is volume that is the property. Do I have any serious physics student who can really convince us as to why it's like that? Yes, they may ask you. The thermometer is constant volume. Then why are you really considering pressure? This thing you're seeing, fixed mass of a gas, this one is constant, fixed mass of a gas. Okay, let me teach you, let me educate you, because you're supposed to learn. I don't see anyone who is ready to educate us. But this is the point. You've heard of gas laws. Gas laws are also under this topic, so we shall talk about them in details when the subtopic reaches. But as of now, let's get the content, okay? So they are what we call gas laws. Gas laws relate about three things, okay? Okay, let me maybe write here. So I was telling you that gas laws relate three things. Who knows those things? Do I have anyone who can tell us the three things that the gas laws really? When I start using the workbook, please use the chance to start taking some notes and also rest a bit. Okay? Now, what are those things? We have pressure, which is denoted with letter P. We have volume denoted by letter V. Then we also have what? Temperature. So it is always PVT. Okay. Some of you have covered some good chemistry. You've looked at this. You've looked at this in chemistry calculations. You know these are moles. This is a constant. So you see the relationship is about PV and what? PV and T. So they always move hand in hand. They never leave each other. Okay. Now, for this case, we are looking at thermometry. So we expect temperature to change. So don't bring your things of constant on temperature. It cannot be constant for this case. Because when you move something from hot water to ice, that is a change in temperature. So don't think about temperature being constant. It's either pressure being constant, okay, or the volume being what? Constant. Hope we are together. Now, let's assume we are talking of gas laws. After all, those thermometers even have gas. Are you aware? We shall look at the images, and the images are so good. You look at them in Tom Duncan. Tom Duncan, that is advanced physics. It's a very good book. It's colored. So the diagrams are colored so they look good. I'm going to send it after here so you all remind me. Yeah, for those reference textbooks, we just provide you all. They are for the country. Okay. Now, if at all you have a certain vessel where you have your gas, I want you people to tell me the fact. So this is your vessel. And of course, you're having gas inside. So we are going to have case 1 and also case 2. We are having a gas. So I want you to be at your school. Your teacher asks, why is it really that pressure is considered for constant volume again? You come out and say exactly what I'm going to say. Yeah, trust me, you leave the audience shocked. Okay? Now that is our vessel. Inside we have gas. So I've said we have two options. The first option is a constant pressure. So that means this is the constant pressure gas thermometer. Then for case 2, I want us to have constant volume. So it is the constant volume gas what? Gas thermometer. Are we together? Now I've said temperature. For it's supposed to change. Yeah. We are dealing with thermometry. We are measuring temperature. So why would we measure something that is constant? So I'm saying temperature must what? Must change. Now, where you're having constant pressure, I want you to listen so much. What if you come and you heat this gas? Usually heat is represented like this, isn't it? What is going to happen? First and foremost, do you people even know pressure? I think let me start from this side. You come and heat. I'm going to just say these words, so make sure you understand. Then maybe you will write them. Because I just want you to understand why it is that thermometric property for that class of thermometer. Now, if at all we consider constant volume, with constant volume, I mean that this vessel of mine is not supposed to expand. But remember, it is a gas. This gas inside, it's having, of course, the molecules of the gas. Gas molecules. So, if at all the volume is supposed to be constant, that means it is not supposed to increase in size. My vessel, excuse me, is not supposed to do what? Increase in size. So what is it? What is going to happen? That for you as you heat, the motion of these ones is going to increase. Are we together? So as the motion increases, they are going to collide so much with each other and with the walls of the vessel. Am I lying? You've tried to hit them. And I'm saying that as you hit them, what is happening? We're having increase in kinetic energy. Okay, let me just put it here. Kinetic energy is to do with motion. So as they move, they collide with each other. They also collide with the wall, with the vessel wall. Yeah. Okay. Now you people, I'm asking, what is really going to happen? Remember, it's not, the vessel is not supposed to expand, volume is constant. But these gas molecules are over colliding with the wall of the vessel. I don't know what is really happening to pressure. Because if we are changing temperature and volume is constant, so we need to ask ourselves what is happening to the pressure. What do you think is happening to the pressure inside? Volume is constant, the vessel should not expand. You're heating, gas molecules are moving so fast because their kinetic energy is increased. They are colliding with the vessel too much. What do you think is happening to the pressure inside? Anyone to tell us? Anyone to tell us? Anyone to tell us in the chat? Someone is like, I'm most interested in the calculations. The reason as to why you think this is not important is because you think it's not important in calculations. And that is the problem I've faced with students of physics. They just want us to come to a class and do calculations, forgetting that it is the content or the science that makes you to understand calculation. This is not math. But even math needs some literature before the thing comes in. So please, you're supposed to be patient with the science that comes before calculations. It's what determines whether they will be okay. So people are like, pressure rises, it increases, and that is right. Okay? Because they are overpressing the vessel, so pressure must increase. Even if you failed and you've said pressure decreases, don't mind. At least you've appreciated the fact that pressure must change. And that is all I wanted you to realize. That when temperature increases but volume is constant, pressure will wisec. Yeah, pressure will wisec and do what? And increase or and change, period. Now the reverse is going to happen this side. That you want your pressure to be constant and you're now doing some heating. And I've told you that the moment you heat, the vessel is going to expand. That is known. Heating causes expansion. And expansion means an increase in volume. Do you understand? I think this one is the easiest. Case 1. Pressure is constant, so we are not minding about how gas molecules are pushing against the vessel wall. We don't want to know. But all we believe, when you heat, gas molecules will expand, and expansion means an increase in what? An increase in volume. So I don't know if people have also appreciated about how constant pressure connects to a change in volume. And in this case, because of heating that causes expansion, volume should also what? Increase. That means the moment you involve a constant pressure gas thermometer in measuring temperature, it will not give you the temperature value directly. Because it is a constant pressure gas thermometer, what is going to happen? Pressure is constant, temperature has increased. What will increase is the volume. Whose volume? The gas. Which gas has a fixed what? Mass. So the increase in volume will give us a corresponding increase in temperature that has caused that thing indirectly. I don't know whether you people are getting. So that is it. If anything is not clear, you just raise up your hand. We say everything. So these ones I'll put 2 ticks. Hope we are together. Okay? Now, pyrometer. Now, when you reach the pyrometer, I even gave you a certain hint here and told you that they don't want the total radiation pyrometer to be considered here. So you even hear the word radiation. But we shall talk about that when we reach it. But for now, have it in mind that a pyrometer deals with what? Radiations. I think you can see. So that arrow is very key in that way. So when you hear of radiations, you people have heard of electromagnetic radiations, and you've also heard of radiomagnetic waves. You've heard of radio waves. So when you see radiations, you immediately think of waves. You like it or not, waves are there. Waves are there. The moment you hear of anything to do with radiation, think of waves. And the common property of waves that we can really use in this place, the one that we chose, is the quality of the wave. And you all know what really relates to a quality of the wave is the wavelength. So we call it like that. Pyrometer to do with radiations. Radiations and waves are just like this. So which property of waves can really come in place? It is wavelength. It is the most common. Most common. When you hear waves, you think of wavelength, period. Nothing much. Is it okay? Now that is all. Now, these are the cheapest things that are coming next because they're the ones we are going to use in the calculations. Let me tell you, calculations are very cheap. If at all, because calculations are all about the steps taken to come up with scales. And you cannot understand scales if you don't understand the terminologies. Do you connect? Those of you who have watched already some classes of physics of ours to do with calculations, we spend a lot of time here. When calculations begin, we just do around 2. Then we go to the assignment and then we check, are they doable? If they are doable, we end the class. Period. Okay? Now, the second terminology, fixed point. Fixed point. Now, all you need to understand about a fixed point is the word fixed. Now, let me tell you this. I'm not going to define for you fixed point now. Why? You don't need to cram the definition. You just need to understand what it means. So as of now, first year of the word fixed point, it's like telling you family. And before they define a family, they have told you we have a nuclear and extended family. So I'm also going to tell you that a fixed point or the fixed points are 2 in physics. We have the lower one and upper one. So we have what we call the lower fixed point. Harmony, I saw your hand up. I don't know if your issue has been resolved. I don't know why it's down now. Was it tired? Then we have what we call the upper fixed point. Okay, we are going to first have those. Okay, let me first hear from Harmony. Then we proceed. I want to give him a chance. I don't want him to think we are very bad people. Yes, Harmony, I've asked you to unmute, so you please speak. We are hearing.
Good evening, sir.
Yes, good evening.
Okay, my question is like, is the pyrometer the same as the temperature gun?
Is the pyrometer the same as the what? I don't know, and now you're muted. I don't know why you've muted. I've not heard the word. Maybe you send it in the chat. Yeah, but I've told you there is when we are supposed to look at these types of thermometers, each on its own. And those are things you can even get from the internet. You ask, is this the same as this? If yes, why? If no, don't answer. If yes, they explain why is the nickname like that. So those are things that shouldn't really stress you as a senior 5, okay? Or as a senior 6. Now, the lower fixed point has another name. You people, you've heard of ice and steam at least. Someone may be there and ask themselves, why do you really relate everything to water in these things, even in chemistry? Why we like water? It's even the first topic in senior 5 biology. It is the first topic in A-level biology, water. And you all know water is life. But that aside, in physics we believe that water is one of those substances that have all the 3 states of matter active. Have I lied? Have I lied? Are you aware that water has those 3 states of matter active? Water when solid is ice. Water when a gas is steam or water vapor. Water when a liquid is liquid water. Or people just call it water. So that's why we like it so much. Because it has that ability to coexist in all the 3 states of matter. So it's that special. That's why we like it so much in physics. Yes, okay. Now, you all know that the lowest point of water is ice and the highest point of water is what? Steam. So don't be surprised when I tell you that the lower fixed point can also be called the ice point. So you can have the relationship that way. especially the people who are learning this for the first time. Many of you requested me to do this. So I want you to get some things from first principles anyway, or learning them by heart, whatsoever you want. Then the upper fixed point, since steam is the highest point of water, we shall also call it the steam what? The steam point. Yeah, so when you see these things, don't be surprised. Now you all know that ice is present at temperatures of 0 degrees Celsius. I know that one. I'm quite sure that you know that. That ice is present at a temperature of what? 0 degrees Celsius. And I believe you all know that steam is formed as water is boiling, because it's now moving from the liquid phase into the vapor phase. And you all know that the boiling point of water is 100 degrees Celsius. All water boils at that temperature. All that is aware. So first understand the types of fixed before even understanding what is happening. Okay? Then I want to add on something. These things are supposed to move in order. Yeah. These things are supposed to move in order. If at all we are to move from the lowest fixed point to the uppermost fixed point, how are we supposed to move? I want you to listen. How are we supposed to move? Oh, let me tell you a secret. Okay? Water is first. Though we shall also talk about this in calorimetry under latent heat, but don't get tired of all this. It is physics, it will still come back, even in your next life. So have it in mind that when you have ice at 0, okay, you all know it will first melt. You understand? And it will become liquid water. So I'll just use water. Have that in mind, and it will also be water at 0. At first, that's what we shall have. So we believe that here, what the ice has just melted. Okay, after melting, it becomes water, but still at 0. So when you come and increase your temperatures, I want you to listen. Yeah, you do some heating. Yeah? You heat the water. So this water will reach 100. So the water will reach 100. I want you to listen. And then the water will eventually become steam. But have it in mind, as the water escapes as vapor or steam, it is still at 100. It can never go beyond that. Are we together? Now, that is how we move. Yeah? That's how we move, maybe from the ice point to the steam point. Now, there are things you're supposed to understand. So when they ask you about the steam, okay, if they ask you about the ice point, please, you take note of this. This is the ice point. Someone may be like, but what do you mean? What you mean it is a change? No, remember it is a temperature, eh? And this is 0, even this is 0, eh? So that's why I'm calling it ice point, because the temperature is still 0. Yeah. Then when we come here, this is 100, even this is what? 100. So I'll come and call this one what? Steam point. Don't look at it as a change. Look at it as in the temperature has been maintained. Eh? So we are still at the same place. When you understand this, you'll be in position to define ice point, you'll be in position to understand or to define steam point. Have it in mind, in the new curriculum, you don't define, but you need the definitions for you to do whatever they want you to do. So never take them lightly. Try your level best to understand the physics, okay? Now let's define and define everything. Now, there is what they call dictatorship in science, eh? Whatever you're seeing down there must happen normally. Whatever you're seeing there must happen normally. But the problem with the word normally, people misuse it. People think it's an English word, but it's a science word with a lot of meaning. But when it comes to these things of temperatures, for me, I change it and say standardly. Yeah. So if at all these things are to happen, we expect them to happen at standard conditions. You may say happen under normal conditions, under normal circumstances, under standard conditions. Now, if I may ask you all, do you know the standard conditions in science? Because we shall need them in heat quantities, we shall need them in heat transfers. Who can really raise their voice and tell me the the standard conditions in science? The standard conditions are two. And you people usually abbreviate them as STP. So when they say standard conditions, they mean STP. And you people know STP means standard, temperature, and pressure. So by standardly, I mean whatsoever you're seeing must happen under what? STP. But since we are talking of changes in temperature, I may rule out the ST for now and first leave it, but then concentrate on the SP. Are you getting it? It is STP, which means standard temperature, which means standard pressure. But the case scenarios we are handling, temperature is changing, so it may not be a constant. So let it first leave our things. So let's first handle the standard pressure. So who knows the standard pressure? I want one science student to tell me all the three values. I need the value in millimeters of mercury. I need the value in pascals. If not pascals, they are called Newton per square meters. Hope you all are aware of those units. I also need the value in atmospheres because we use all of them in physics. So you need all of them, even in chemistry. Sorry for those who don't attempt it, but they are needed. So I need someone who is going to give me these values. Do I have anyone who does? No one is raising up their hand. Chances are high that whoever wants to respond is going to copy. So let me give you those values. So the value of standard pressure in millimeters of mercury is 700 and what? And 60. The value of pressure in terms of pascals or the Newton per square meters, it is 101, 325. But remember when I was teaching you measurements and dimensions, I told you physics, they like standard form so much. So don't be surprised when they give you values, especially this one of pascals. They can decide to give it to you in standard form. And I told you what standard or scientific notation is, and I will not repeat. Then in atmospheres, it is strictly what? 1 atmosphere. So all those values mean the same, they just differ in unit. Okay? So that is standard pressure. You all know why standard temperature is out for now. So whatsoever is happening above steam point, ice point, it is happening standardly, and that is the stuff. Now let us first define them, and then we define fixed point, then we go to triple point, we talk about the absolute zero, then we go to the scales. We do the scales, we do the calculations very fast. I give you research work, we leave this place. Okay? Now, let's first define ice point. So for me, I just believe that ice point is the same as lower fixed point, and you know that the temperature is 0. That one I will not repeat. They are saying that this is the temperature at which pure ice can exist in equilibrium with water at standard atmospheric pressure of that. What I believe, all of you know that it is a temperature. That one I accept. All of you, I believe, understand what we mean by pure ice. You all know what we mean by the water. You all know the standard conditions. I've talked about them. But then this word equilibrium, for you think it is a small word. But let me tell you, you can reach an exam and you cannot recall the word that was there. You end up putting something funny. So let me tell you what equilibrium means. When you go to Google or anywhere and ask the definition of equilibrium, they will tell you that this is a state of balance. Yeah, they will tell you that this is a state of balance. Like things trying to balance, that is all. That's what they mean by equilibrium. So I want to teach you something. Remember, I want you guys to agree with me. Remember, ice is becoming water. Then this water later becomes what? Steam, isn't it? But remember, ice is becoming water through melting. But remember, the water can also go back to ice through freezing. Are we together? Water is becoming steam through vaporization or evaporation, but the steam can condense and get the liquid water back. Are you trying to understand? So remember, this is solid, this is liquid, this is what? Gaseous. Now, this state of balance, I don't know whether people are seeing this. Are you seeing that? When you ask people how do we call those arrows, they will say partial arrows. But as you progress, especially those who watched the lesson on chemical equations where I taught you partial arrows, I remember telling you that these ones are for reversible reactions. A reaction which can go back and forth. So that thing of back and forth, going back and coming back, tries to bring out some sort of balance, okay? It tries to bring out some sort of equilibrium. After all, equilibrium is a state of what? State of balance. Hope we are together. So when they say the ice is existing with water at equilibrium, understand that the word equilibrium is coming from balance. The balance is coming from the partial arrows. Partial arrows are because of the melting that can later be reversed as freezing. It's because of the evaporation that can be reversed by condensation. Are we together? So that's the equilibrium word. Never forget it. Then when we come to steam point, look at our sketch. When you look at our sketch, steam point is that water that is becoming steam. Are we together? So when you come and read it here, what are they saying? They are saying the water is becoming steam from our sketch. Then these people are saying that the water and the steam or the water vapor, they are existing in what? In equilibrium. And we agreed everything happens under standard conditions of pressure, and that was the value we stated, isn't it? And it is corresponding to a temperature of that. I don't really think that is hard. Now, after defining the two types of fixed points, now we can go and define fixed point. You have realized that fixed points, we are having existences in equilibrium, we are having states changing, solid becoming liquid, liquid becoming gas. So we are having states changing, but at specific conditions, where one of those specific conditions is 760, which is the standard condition of pressure. Are we together? So when you come to look at the definition of fixed point, it will make sense. Sorry for my tongue, but I mean fixed point. So they are saying it is the temperature. So even when they call it a point, for you understand it is a temperature. How? Lower fixed point, ice point. Ice means 0 degrees Celsius, which is a temperature. So points are temperatures. What is happening? A substance is changing states. Ice point, ice is becoming water. Steam point, water is becoming steam. And it is happening under specific standard what? Conditions. Do you see that that definition would be hard if we first defined it before talking about its types? And that is it. So the moment they are used down there in calculations, understand ice point 0 degrees, steam point 100 degrees Celsius, okay? Then what I shouldn't forget, they can give you these things in kelvins. So don't just cram these things anyhow. They can give you these things in kelvins. So you should be in position to know how kelvins and degrees interact. But I believe some of us already know this, yeah? That if at all you want to convert something from degrees, okay, that you have a certain temperature, small t in degrees, okay, and you want, let me educate my favorite scholars. You're having a small t, that is temperature in degrees Celsius, and your goal is to convert that one into a certain temperature in kelvins. I remember teaching you in measurements and dimensions that small k is for the kilogram, then capital K is for kelvins. Okay? Because Kelvin was a person, but kilo, I don't know about kilo, whether he was a person or not. Now, if I told you having your small temperature in degrees Celsius and you really want to convert it in kelvins, just simply add 270 to what? To it. Remember, these ones are also degrees Celsius. Okay, let me just remove this. Okay, just add the 273. Just add it. Then the temperature will become kelvins. What do I mean? That if it is ice point, remember ice point is 0. So the 0, I can add the 273 to it. and I come out with finally 273, but in kelvins. So when you find a textbook telling you that this is the ice point, don't be surprised. Then when we come to steam point, you all know that we have agreed, okay, I said it is 100. But I've said for you to convert degrees Celsius to Kelvin, simply add what? 273. And what will be the result? 373. And this will be in Kelvin. So when you find a book telling you this is the steam point, I don't want you to argue. Just accept and appreciate the applied concept. So that is about those 2 points, and we are going to meet them so much in this very session. So let me secure our document. It is thermometry. Yeah. Now, okay. Now we go. The next is the triple point of water. We have talked about a lot of points: ice point, fixed point, steam point. It's high time we talked about the new guy in the building, and that is triple point of water. The moment you see triple, what comes to your mind is number 3. So what is all about this theory? That the 3 states of water are actually present. Yeah, the 3 states are present. So when you see triple, triple is single P, please. People have a tendency of making it double P. It is not. It is strictly and strictly single P. So when they say triple, they mean 3. So what is all with this theory? The 3 states of water are present. I told you a point is a temperature. Here they are just making it, they are just exaggerating. This is now cosmetics in science. They are saying it is a unique temperature. But even when a student says it is the unique temperature, okay, it is the temperature, it is okay. Or a unique temperature. And what is happening? The 3 states are existing. They are present, they are coexisting, but I told you it is in what? In equilibrium. Yeah, that steam can eventually become ice through condensation and then freezing. That ice can eventually become steam through melting and then evaporation. Are we together? So they are saying that at that triple point, which is a unique what? Temperature, we are having pure ice, we are having pure liquid water, or you can just say pure water or pure liquid water, and then pure water vapor. All of them are existing together, or what I call coexisting in equilibrium. Yeah, coexisting or existing together in equilibrium. That temperature, is it really hard? It's not hard. So since it is a temperature, this is its value, and we are going to meet it so much. Don't ask me why it has that 0.16. Don't ask me. That's the standard value from books. Okay? And when you argue, we open the books. I moved with my Neocon and Parker, my best friends, and also my father, Roger Muncaster, and then my bestie, Tom Duncan. Yeah, for him, he made a colored book, things to do with lucky. Okay? Now, let me even just write it here for no good reason. A very big value, just to make sure that you don't really forget. So I'm here to tell you all that 273.16, we are going to use it in calculations. Even in your assignment, you're going to come across it. So this value, have it in mind, it is in what? It is in kelvins. And when you see it, just tell the people around you that I know that value and it is the triple point of water. And also tell them triple, it is single P. Yeah? Tell them about it. Tell them since it belongs to water. Okay, tell them triple alone means 3. Since it is a point of water, that means the 3 states of water actually coexisting in equilibrium. And since it is a point, that means it is a temperature. And which temperature is that? This is the theoretical value. And that is all. Okay? Now, lastly, absolute zero. Someone may be like, plus they taught us it, they didn't even talk about absolute zero. What is really that? Does it even have calculations to do with it? No, but at least you need to know something about the absolute zero. I even need you to go and watch a YouTube video about it. It is a very good value in physics. Yeah, it is a very good value. So absolute zero is the lowest possible temperature. Yeah, You just tell your parent there near or anyone. Tell them, did you know that there is a temperature below which we cannot have any value? It is the absolute zero temperature. It is the lowest possible on Earth. I don't know about other planets, but as far as Earth is concerned, it is the lowest possible temperature. You cannot find any other temperature below it. And why they call it zero, it's because of 0 Kelvin. So that temperature is 0 Kelvins. So if at all you read any textbook and find any temperature in negative Kelvins, you throw that book. It is not for your curriculum. It's not a book of planet Earth. Because the lowest possible temperature, absolute zero, is 0 Kelvin. That means we cannot have anything below 0 Kelvin. So we cannot have Kelvins in negatives. So when you calculate anything and get your answer as negative Kelvins, that is bad. Yeah, we cannot have that temperature. That is really bad. So when you convert those Kelvins to degrees Celsius, if you know math, you will end up coming up with such a value. Okay? And that is the value that you want. That is the value that you want. If for you calculate and you come out with 273 alone, I don't know about that. Okay? Um, there is something I want us to talk about, but that will be when we begin calculations. But I don't want any of you to be surprised. There are calculations. You see, textbooks are so many, but they call them reference books for a very good reason. We are going to do some calculations, and you're going to see me simply adding 273 because that's what we do. But you will find books of physics that add 273.15. If at all someone lands on your work and they don't know physics, they will cross your work. But as far as your curriculum is concerned so far, that's what they add. Just add 273, period. Don't overthink. But as far as absolute zero is concerned, you take the value I've given you. Okay? Now, we have now moved, because now we are moving to temperature scales. And when temperature scales are done, it is just one page. It is just one page, then calculations begin. Do you see? Examples are here. Those people who are interested in calculations, stay on for 5 minutes. We explain the scales, we begin calculating. We are going to do few numbers, and then assignment is just here. You see the assignment? Yeah. And the moment I give you assignment, I tell you what we are going to do for this chapter, which is yours. Take home. I guide you, and then we leave this place. So let's stay on, and we look at the scales. Very cheap, very cheap, very cheap, because whatever we have been talking about is really coming back. So now you listen, and take note. Okay, now what are they saying? So the very first chapter under the topic 9 is temperature scales. Okay, and they are saying this is a scale used to measure the degree. So remember we said temperature is a number, so that number is going to be gotten from a scale. As simple as that. And you all know if it is okay, you all know everything bases on a thermometric property. I don't want to go into that. Those scales you see on thermometers, they are the ones we are going to learn today. So, what are the types of the scales? The scales are two, and I've already educated you. We have the centigrade scale and the Celsius scale. Sorry, we have the Celsius and the Kelvin. We have talked about that. But they have other names. So the Celsius, this was a person. So the moment you write Celsius, I think he was called Anders Celsius. You can check on Google, I'm not so sure. But I think he's Anders Celsius. So this was a person. So why I'm telling you it was a person, you're supposed to use capital C. So never think of small c. The moment you write it, that means you're not from Science Scholars Academy. That will be quite absurd. But the other name, you can call it the centigrade. Then Kelvin, this one I've overtold you, it is supposed to be capital what? Capital K. But it's having some other names. It can be called, if you don't call it the Kelvin scale, you're supposed to call it the absolute temperature scale, or the abnormal scale, or the thermodynamic temperature scale. Are you listening? If you don't call it the absolute scale, you call it the Kelvin scale, abnormal scale, thermodynamic scale. Now, you're supposed to learn why do they really call them like this? And I'm going to educate you still. Why they call it the thermodynamic temperature scale? We shall see this when we reach thermodynamics. I told you it is a chapter or a topic under the branch of science, heat. Okay? Then, why do they call it abnormal? You see, physics scholars and educators, for them, they believe in degrees Celsius the most. So for them, they believe a normal scale should begin from 0 degrees Celsius. Even you, that's what you thought. So they call it abnormal because it begins from 0 kelvins, not degrees Celsius. So because it begins from 0 kelvins, and 0 kelvins is the absolute zero, that's why they call it absolute temperature. Do you understand? I want you to be among those few students who can tell why the Kelvin scale is called abnormal. You tell that person. Physics scholars and educators have rugezigez. For them, they want a normal scale to begin from 0 degrees Celsius. But that of Kelvin, for it begins from 0 Kelvin, so they call it abnormal. Then tell them why do they also call it the absolute scale. Tell them because it begins from 0 Kelvin, which is the absolute zero temperature. Why Kelvin? The units are kelvins. Why thermodynamic temperature scale? You see that in the last chapter of the branch, which is thermodynamics. And you also appreciate it. Okay, so that is it. So we are now going to begin with the first one. Celsius, why capital T? Under Celsius was a person. I don't remember the year. I read those years in Nelcon and Parker. I don't recall, but I think it was in the 1700s. Those years, that's when the Celsius unit came in. But it has been years since I last read those things, so I may not be accurate to that unexaminable stuff. Okay, now let's begin with the centigrade and the Celsius. So there are two things that you really need to appreciate here. These temperatures are supposed to use fixed points, okay? So as a student, you should know that this Kelvin scale, for it will use the triple point of water. You get the triple point of water. It will, or even if I just say triple point or triple point of water, it will be it's what it will use as its fixed point. So the other thing I want to tell you that these scales, the most important definition, what really defines them is that they must have fixed points. So that's the first thing you're supposed to think about when you hear of the word scale. So I've said they must have fixed what? Fixed points. And I'm saying for the Kelvin scale, its fixed point is the triple point of what? Of water. And then for the centigrade, I expect people to be here. Tomorrow is a Sunday, so no school. So stay here, we study. I just thank you that you've tried to maintain the number somehow, somewhere. Okay? Though not so good. So the Celsius or centigrade also has the two. For it has two of them. For it uses both the ice point and the steam point. Okay? Since it takes the steam and ice point, the Kelvin scale says, no, for me, I will not copy you. For me, let me use the remaining point that has really remained, and that is a triple point of water. Let me take on that. And it takes on that. Okay? We go. What are they saying? They are saying that the centigrade or the Celsius scale is a temperature scale, of course we know. It uses ice points or degrees as its lower fixed point. Don't you know that? And the steam point 100 as the upper fixed point. That means that scale goes from 0 to 100, period. All those are the fixed points it's having. Okay, you note that. You keep quiet. They are fixed. This word fixed, you're supposed to understand it as an English word. Fixed, it is fixed. So even in the steps we are going to follow in the lab, We shall fix those temperatures, so don't be surprised when we just fix them and we just fix them into the procedures. Okay? Now, the next thing are the steps. Now, the lesson has just started. All those who are saying, for us, we are interested in calculations, what? This is the time. This is the time. This is the what? The time. This is where the classes begin. If at all you cannot set up the scale, my dear, you cannot calculate. To prove you wrong, I want you to read this statement from your syllabus book. I got time, I read the syllabus book word per word. So believe what I say. And for me, when I read, I understand. They say derive expressions for different temperature scales, their interrelations, and use them to solve numerical problems. So if you don't understand the temperature scales, you will not understand the interrelations, you will not be in position to use them. That's why calculations are giving you a time. Because for you think the teacher woke up one time, came to class, and put a calculation to be solved. My dear, that's not how science works. Science follows content protocol, which protocol you must respect, both as tutors and the tutor's audience, okay? So you listen extra carefully. Now, someone may be like, but what are we really doing here? Hey, what are we really doing here? We need to know. Let me teach you. Let me teach you. Let me teach you. This is our workbook. You want to get a Celsius scale, yeah? Or you want to get any scale. This is what happens. This is what this is what these people mean by getting a scale, okay? Remember, for you are aware that maybe we are moving from 0 degrees Celsius, are we together? Up to 100 degrees Celsius. I want you to listen carefully. I want you to look at the liquid in gas thermometer, the one you looked at. You guys, do you recall that we are varying the length? Do you recall that the length of the liquid column was the one changing? If you don't understand that, I want you to look at this question. So we shall meet it again. That means it is the question you will understand the most. I want you to read this. They are saying that the length of the mercury column is 2 centimeters at ice point, then it is 2.73 at steam point. Do you see that these thermometers can never measure temperature directly? They first measure something which is a thermometric property. It is that thermometric property to now link us to the temperature. Just like the way you see it is these centimeters that linked us to 0 degrees, the ice point. It is these centimeters that linked us to, I don't know whether people are getting it. So that's what really happens. So I want you to look at something like that, okay? And this is it. So the 0 degrees is known. That's why I told you that these ones are called fixed points. Eh? And I told you by fixed, maybe you can take it that they are known. Okay? Fixed that there. Why am I saying known? I think I'm obsessed with what I'm going to explain. This is known. And this one is also fixed. It is steam point. So it is a fixed point. It is a fixed temperature. It is known by everyone. Someone may be like, where am I going to get degrees Celsius? Remember, you are in the lab. You want to come up with a scale. That's what we are doing now. So you listen. Okay? I don't want you to be students who are going to cram procedures. Because procedures, you like it or not, you need them to handle scenarios. Okay? So you listen carefully. So someone may be like, if at all I'm in the lab, where am I going to get the 0 degrees Celsius? Just simply get water from the tap, put it in the fridge and form ice. The moment you form ice, that ice is simply at 0 degrees Celsius, okay? If at all you're looking for 100 degrees Celsius, it is very simple. Get water from the tap, boil it, let it form water vapor steam. The moment you get the steam, that means we are there. Boiling water to form steam, we are there at 100. So those temperatures are really easy to create in the lab, okay? What do? You get your thermometer liquid in glass. I want you people to listen. The thermometric properties you recall, I think you recall EMF for the thermocouple. You recall length of liquid column for the liquid in glass thermometer. You recall electrical resistance R for the electrical wire or the platinum wire for the platinum resistance thermometer. You recall wavelength for the pyrometer. And you recall those things of constant pressure, constant volume. You recall those things. Now, this is what you do. You go to your lab, you put there your ice, you put there the thermometer. Are you listening? The thermometer can be liquid in glass, it can be platinum resistance. When it is, I want you to listen carefully. So that means you need to understand which thermometric property you're going to use. Yeah. So for me, I'm going to say thermometric property since we are not sure. Since we are not sure of which one we are using, remember there are so many, eh? So we are going to give them a general letter in math, which is X. They usually use X for those unknown stuff. But there are many. L for liquid, R for resistance, P for pressure, V for volume, EMF, and lambda for wavelength. But for me, I've just said X. So I'm saying that you're supposed to first get ice, put it there in the lab. Are we together? Get a thermometer, dip it. When you dip a liquid in glass thermometer in ice, you're going to get first the length of the liquid column. Are we together? That's what you get first before reading the. Remember, even the temperature is known, it is 0. Are you people getting me? It is 0, you know it is 0. So what you're going to get is going to be the value of that thermometric property at 0. So I'm putting X naught. Are we together? Then after that, get that thermometer, put it in steam, boiling water whatsoever. That means you're going to get the value of the thermometric property at the steam point 100. Are we together? Are we together? So this one can be length at 0, okay? Remember, any thermometric property. If it is a pyrometer, it can be wavelength at 0. If it is a platinum resistance thermometer, it can be resistance at what? At 0. You understand? If it is a pressure, if it is a constant pressure gas, that can be the volume at 0, things like that, and so on and so forth. Hope we are together. Then, even this side, the same thing. If it is a liquid in gas thermometer, it will be the length of liquid column at 100. If it is a constant pressure gas thermometer, there it is volume of a fixed mass of a gas. So it will also be the volume at what? At 100. Then if it is the platinum resistance thermometer, you know what we are going to have for that case, okay? So we shall have, you're not supposed to cram these things, okay? Like that. Are we together? Now, all you want, you're trying to set up, yeah, a scale. You're looking for a certain temperature. Now, after that, you get any water. Are you listening? You get any what? Any water. Remember, this any water you're getting, you don't know the temperature. So the temperature will put theta degrees. Someone may be like, but won't I read it from the thermometer? Remember, when you use a liquid in gas, what you will get first is length of the liquid column. It's the one to connect you to the temperature. So meanwhile, you don't know it. Are you listening? if at all it is a platinum resistance thermometer, what you will get first is the resistance, the ohmmeter inside that thermometer will measure first before you get the corresponding temperature that caused that change. If it is a pyrometer, you will first obtain the wavelength. It's what will connect you to the corresponding what? Temperature. We are together. So this one is any temperature. Since it is any water, any tap water, this one is unknown. Okay? Unknown. But remember, it is going to give us the value of the thermometric property, but at that temperature, which we don't know. You understand? Yeah. That value for it will be provided. Yeah, because we shall read it from the thermometer. If it is length, we shall see that length at that unknown temperature of that water we have gotten from the tap. If it is the constant pressure gas thermometer, we shall get that volume. For the gas, maybe we have obtained from a plant. Do you know that plants release gas during photosynthesis? So trust me, when you get a polythene bag that is not porous and tie it around a leaf for 6 hours, you collect some gas. Then if it is maybe the platinum resistance thermometer, you can also get the resistance of that tap water you've gotten at a temperature you don't know. And then maybe, do you see that the property connects us to the temperature? That's what we meant, that thermometers need their properties to be in position to measure temperature. Okay, now what do you do after that? What do you do after that? You plot. Someone may be like, what am I going to plot? This is it. Remember your temperature was what? 0 degrees Celsius. And it gave us the value of the thermometric property x naught, meaning x at 0. Then this side, you had your temperature as what? As 100 degrees Celsius, okay? Then you got the value of the thermometric property x at 100, which is that. Then you also got your any water from the tap, which was at an unknown temperature theta, and it also gave you the value of the thermometric property x what? X theta, like that. Are we together? Then after that, you plot. Do I have anyone? I don't know why people's videos turning on. Let me try to help them. I think you're supposed to remind me before we have the next class. I need to turn off that setting. It's really disturbing so many of you. So you all who are on, check your videos. Many of you are having videos on. Check if your video is off. Make sure that thing that is having video, it must have that red line through it. Yeah. Because you may end up exposing some of your side hustles that we may not need to look at. Okay. Now, you're supposed to plot after that. You're supposed to plot after that. But remember, I told you, this is it. This is it. This temperature was known, okay? This one was known. Because they were unknown, we could read these ones from the table. Okay. These ones are read from the thermometer, so these ones are always available because the thermometer has the ohmmeter that is going to measure resistance. We have the idiometers that are going to measure volume. We have the pressure gauges that are going to measure the pressure, the barometers, okay? So these ones, for them, they are always available. I will just put a tick on the values of the thermometric property. But the only unknown we have is this. Are you seeing that one? It is the only unknown we have. Because we just got the water from the tap, we didn't know the temperature. But on putting the thermometer, a value of the thermometric property could come, and it's the one to link us. Okay? So I've said we are supposed to plot. And those are the values we are plotting. So if at all you know how to plot, this is what we shall do. I'm going to just have a sketch here. So you people, you know that this is the y-axis and this is the x-axis. Where are we supposed to put temperature? Are we supposed to put temperature? Remember, we are plotting two things. Temperature, then the value of the thermometric property. So where are we supposed to put the temperature? Y-axis, x-axis. Tell me in the chat, where are we supposed to put temperature? Where are we supposed to put temperature? You see someone in the chat has triple as double P. Please correct that. It is single P. Where are we putting temperature? X-axis. Thank you so much, Alfred. Those who are saying Y-axis, it is quite absurd. It is quite absurd. It is quite absurd. But it is okay to have it anywhere. For this case, because we talked of things changing linearly and so on. Okay? But it is not okay to have it anywhere. Let me correct that. Because people may misget me. What we put on the x-axis is the independent event, or what you call the independent variable. You people, for the liquid, for the liquid column to rise, it is because of the temperature or the heat that caused the expansion. So the length of the liquid column, it rising and falling, depends on this temperature, which may cause expansion and what? And contraction. That means temperature is the independent thing. So temperature always causes those thermometric properties to change. When they say, that's why they tell you that rate of photosynthesis with the variation in carbon dioxide concentration, because photosynthesis depends on carbon dioxide. I'm using that example because that is O level and all of us did biology at O level. You understand? So the independent variable is supposed to be on the X. So all of us, I expect temperature to be this way down. So I'll put temperature degrees Celsius. Then here I'll simply have the value of the thermometric property. Okay, so I'll say value of the T property. Okay, and I'm saying that the temperatures we are putting in place are very few. Okay, they're only three. The first temperature, which is 0 degrees Celsius, okay? The other temperature, which is 100, and then some random temperature we are not sure of. And we decided to call it theta. Is it okay? Then we said that at 0 degrees Celsius, we shall get a certain value of that property. We shall get the value of that property, we like it or not. And we say that that value is going to be x naught. That was said. That one shouldn't. It is non-negotiable. So the value will be the one corresponding to 0x naught, okay? Then we said that this temperature will also cause a what? A certain change in the thermometric property. But this is what I want you to recall. That we said that a thermometric property varies linearly and continuously with temperature. That as temperature changes, even the thermometric property does what? Changes. Okay? Things like that. So you're not supposed to be surprised in the end when we have something that looks like what we are going to have now. Okay? You all know that if it is length, the higher the temperature, the higher the length of the column, things like that. Very cheap things, okay? So we expect this one to cause a change that is x theta, but maybe it should be somewhere there like that. Then also the 100, this one, we expect it to cause a change, but it should be slightly higher, which is x 100. I'll put it there. Because we expect you increase the temperature, even things get higher. So if we are to plot, you come, you have that dot, you have that dot for those two. Hope people know what I mean by plotting. Then you also have these ones. You people, I'm plotting like this. This one with that one. Then this one with this one. Okay? That's what I mean by plotting. So let me remove these ones. Then after I join those points. So on joining, this is what I'll get. Are you seeing that? So that's what we even meant by linearly and continuously. Linearly and continuously. Those are things you're not supposed to do what? Forget. Linearly, continuously. Okay. Now, with this, you cannot fail. Now, the only challenge you're going to face here, if you're this one student who doesn't know what they call coordinate geometry. If at all you cannot get gradient using 2 points. If you cannot get the gradient, then I think it is quite absurd. You're going to find issues, but let's try. You all know that this point here down, it is called 0, then x naught, isn't it? Then this one here, it is called theta, then x theta like that. Then this one on top, it is called 100, then x 100, isn't it? You all know that we name these points as xy. You tell me, what is the formula of gradient, or what we call slope? Is it change in y over change in x, or change in x over change in y? You just write y over x, or you write x over y in the chart. How do you get the slope or the gradient? So I was trying to show you why we are writing those coordinates like that. We begin with what we are having on the x-axis, then we put a comma, and then we put what we have on the y-axis. The x value is called the x coordinate. The y value is called the y coordinate. All together is what they call a point. That's why they tell you that what they plot are points, and then they connect them to come up with a graph. Okay. Let me see what people have said. Y over x. Thank you so much. Those are concepts that they even teach at O level. So people are saying that slope or what we are calling gradient, people are saying it is the change in y over the change in x. So have it in mind that that K symbol is a Greek letter called delta. Yeah, it is called delta, and it is read as change in. You understand? Yeah. So when I write delta y, I mean change in y. Delta x, I mean change in what? Change in x. Hope that is very clear. Now, there are so many ways. There are so many ways you can have this gradient. Do you understand? Now, there are 3 points, so I can choose any two. Yes, I can choose any two that I want. Any two that I want. And I want you to listen very carefully. But I want to give you a certain hint. You see, zeros are always good. Why zeros are good? Because they really make our life so easy. What do I mean? Remember, you're supposed to say y2 minus y1, isn't it? Then you're supposed to say, okay, in whatever we are going to be doing, let's at least involve the zero, because it is going to simplify our work. So we are going to use two sets. Okay, we are going to use 2 sets, but each set should at least have that 0 coordinate. Okay, the 0 coordinate, I mean this first one. This one at the origin, very important. Okay, now, and it is better for it to be our x1. You see, there are things you're supposed to appreciate, that if you're having something like 3, 4, and then you're having 0, 5. If at all you say that this is x1, y1, x2, y2. When you say x2 minus x1, you're going to have 0 minus 3, which will give you a negative, which is very bad. So if you can, at least you make these first ones. A negative is very hard to deal with. So every time you get a chance to ignore it, please avoid it. You make this your x2, provided you communicate, your work will be marked because you get the same answer. So that when you say x2 minus x1, it is 3 minus 0, which is a positive 3, and positives are very good to deal with. So I'm going to bring that racism here. Yeah, and I'm going to apply it here. So the first set I'm going to use, I'm going to call this one my x1, y1. Then I'm going to call this one my x2, y2. Hope you're following. So if I'm to get the gradient, I'll say, I'll say y2 minus y1, which is x naught minus x, that one. Then I divide by x2 minus x1. So I'll have theta minus 0. So do you see that theta minus 0? Do you see it becoming theta? So that's how good zero is. Eh? It tries to leave some breathing space for us. Then let me go for another set. So as I come to another set, I will leave the x1, y1 on the zeros. Then I gonna also use code the other one up. I'm going to use green. So it's now going to be our x2, y2. Someone will be like, why all that? We really need it. Because now you're supposed to memorize these formulas so that you just use them in calculations, but also understanding the derivation. The learning outcome is saying derive. So you are supposed to really derive. Okay? Y2, what is my Y2? It is x100 now. My Y1 has not changed, it is x0. Okay? Then I divide. When I say Y2, then I say x100. Hope you guys don't get confused. You should be very sober. Divided by x2. What is my x2? It is 100. What is my x1? It is a 0. Do you see that 100 minus 0 is going to remain 100 and things are going to become easy for us? Things like that. And they are very cheap. Oh, that is gradient or that is slope. So I'm now going to come out and first simplify this. Are you seeing this? Then I will have x theta minus x what? X naught divided by, what do I have? Down I'm having theta alone. Then the other side I'm having x 100. Then I'm having x naught. Then down I'm having only what? 100. Then I want you to recall what I said. I told you that those x's you're seeing, those are values of thermometric properties, which we are supposed to get from the thermometer. For them, they are always available. That's why previously I put ticks on all of them. All the values of the thermometric properties, they are always available because we are reading them directly from the thermometer. If it is resistance, pressure, volume, length, we just read them. Then also this 100 is known. But remember, this was temperature for the tap water. This was temperature for the tap water that you just got anyway, yeah. So trust me, that one is unknown. Yeah, so we don't know it and it's what we are looking for. So since it is unknown, then we are supposed to make it the subject. Yeah, make it the subject. These are one of the topics in O level that really made me to love math those days. Things to do with making a subject. They are really nice. So do I have any student that can really fail to make theta the subject in this case? Can he really fail? Do I have anyone who can really fail to make theta the subject in that case? Because to me, I see it as something very cheap. But let's not just ignore it or take it for granted. Let's give it a try. Let's give it a try. Okay, now if I told you to make theta the subject, you know they always say, okay, the good thing is to first cross multiply. So let's say we have cross multiplied. Let's say we have cross multiplied. Pray for our network. Pray for our network. We may really get issues, but pray for our network. Okay. Let me hope at least you can try to hear something and hope the screen is clear. Now, I've told you that let's first cross multiply to really make other things easy for us. So we are going to come and say that this one will be something like 100. We are cross multiplying, and 100 will be multiplying this. Okay. And then the other side, I told you the lesson is going to be long enough, but after all, tomorrow is a Sunday, so we just need to be here and stay and be patient. Then theta will multiply x, so it will be like that, minus, then we shall have the x naught here, something like that. Okay. Then remember, we are supposed to make theta the subject. So making theta the subject, it is very clear. We are supposed to just come and eliminate the whole of this. Hope the break we had didn't confuse you. You know where we are coming from and where we are going. Okay, so I'm going to come and say throughout, let me divide by this. Throughout, let me divide by that x naught. Okay. Of course, you know, the other side, it's going to be cancelling. Okay. But then if it cancels, I have a chance. Okay. If it cancels, I'm going to come and say, you know that this one is cancelling. Hope you can see that. So I'm remaining with theta alone, the other side. So I can now transfer it to the left. So this side, I'm having x theta. So I'm copying this here, x theta minus x naught. Okay. Then what do I have down? I'm having x. It's going to be what? 100. Then also minus x naught. And if you realize, this will be times what? 100. Like that. And remember, we are dealing with degrees Celsius. Why? We started from ice point, steam point. So that means the whole temperature we are going to be getting here, you like it or not, you will be obtaining it in degrees Celsius. Or you will have obtained it in degrees Celsius. Hope we are together there. So this is how you can obtain the unknown temperature. And that's what we are going to be using in all calculations. So that will be the unknown temperature, and that's how we shall calculate for it, unknown temperature. So I want you to just look at the derivation we've had. Sorry for that network disturbance we had. Yeah, our fiber went off and it went back on. I don't know if you guys were disrupted, but I want you to just look at all that summary. All I know, you can't take a screenshot, but at least I believe the words are clear. I want you to go through them. Those are the steps we are going to be following throughout. Even the calculations that people claim are hard or that are giving people hard time, trust me, they are all rotating around there. Remember well why we let the thermometric property to be x. Remember the ice point and the value, steam point and the corresponding value, then any unknown value and the value we are going to read from the thermometer, and how all the rest are known apart from that unknown temperature. About how we plotted, how we brought in the concept of slope. If you look critically at this point, let me use the wrong, okay. If I use something wrong, I may end up confusing some of you. But I mean this part, I don't know whether you're seeing that arrow. Are you seeing that part? I just try to extract out this. Then I try to simplify by ignoring those minus zeros. Then I later made theta the subject. And I'm saying that theta is the unknown temperature. Okay? So I just want to see around 2 people telling me in the chat that we are good. If we are good, we proceed. Let me tell you, we are done. Like we are done. All questions are going to be like that. Because now the triple point, for it is the easiest. It is actually nothing when it comes to the Kelvin scale. Remember, we said now we are dealing with the Celsius scale. But now someone may be like, what of the Kelvin scale? Remember, we said for Kelvin scale, for it goes for triple point. For the Celsius, it goes with the ice and steam, leaving nothing for the Kelvin other than the triple point. Let me see what people in the chat are saying. Okay, good to go. That is good, of course. Now, before you guys forget, I want you to understand that this X is the value of the thermometric property, and because of that, that X can be P. Let me begin. It can be L for liquid in glass thermometer. It can be P for constant volume gas thermometer. It can be V for constant pressure gas thermometer. It can be R, which is electrical resistance for platinum resistance thermometer. It can be EMF, and EMF we shall just use letter E, okay, of course for the thermocouple, and it can be lambda, of course for the pyrometer that deals with the what? With the waves, with the radiations, with the wavelength, or what they call quality. So don't be surprised. So depending on the question we are doing, we can remove the X and put any of these letters, any of these letters, any of these letters, any of these letters, and then the things move. Now, remember, you're not supposed to derive this thing every time you're calculating. You're supposed to have something that can maybe help you recall the formula. And this is what I usually advise my students. So without looking at that formula, let me show you. This is what you can do. Maybe if you want to recall it, because there are so many things and so many formulas you're supposed to get in physics. So one formula shouldn't be giving you a time. So it's supposed to be like, okay, I'm looking for unknown temperature. So you put that, then say equal signs. Then you be like, at least I know that there is a division sign here, okay? Then at least you know. So I'm going to put all the common things in black. Then at least you know that this is going to be times what? Times 100. And the overall temperature I'll be getting shall be in degrees Celsius, okay? Are you following? We are trying to get how this formula can be memorized. Then also be like, and I know that this one is minus, even this one is minus, and it is minus the same thing. It is x naught and x naught. So if it is L, L naught, L naught. You understand? And if it is R, it is R naught, R naught. If it is V, V naught, V naught, P, P naught, P naught. Are we together? Then you be like, this is the only difference. You understand that the difference is only there. So if the difference is only there, you ask yourself, what are those things remaining? You're remaining with the thermometric property at that temperature, which is x theta, and you're also remaining with the value of the thermometric property at 100, which is x 100. It is only those ones missing in whatever we derived or obtained in the experiment. So the question is this one going to be up, or it's the one going down? So that's the only debate I expect you to be having every time you're trying to get the formula. Okay? And then you people know. Remember, you're getting theta. This theta you're getting, it's like theta over 1. Yeah? You're getting theta, and you all know theta is the same as theta over 1. So it's x theta will also be on top. You get? It's like you're getting theta, but theta is like theta over 1. You understand? So theta is on top. Even x theta will say I want to be on top. Then 1 is down. Even 100 will say I also want to be down. You get? Things like that. I don't think that is hard. Can you try to recall that formula without going through those derivations? Yes, we derive. But as we calculate, we really need to be recording this formula very fast without panicking. But that is general. You get? So I've told you that this one can be what? Can be L, can be P, can be V, the same way I explained. So it's what we are going to check on through our notes. We talk about the Kelvin scale. It is the simplest and cheapest. Then we calculate. And let me tell you, we don't even need to calculate. We don't. If you understand the formula, how everything comes about, let me tell you, we don't. So maybe just for fun, let me give people a chance. What if I'm talking about the platinum? Okay, for me, I'm going to tell you only about the platinum resistance thermometer. Platinum resistance thermometer. Even if you just go to Google and put in PRT, platinum resistance thermometer should be among the options. So you all know this thermometer uses a thin electrical wire made of platinum that must conduct electricity, but the conducting electrons experience electrical resistance, and it is R, okay? So R is our thermometric property in place. So I want someone who can unmute, and you had a pass. You just talk as I write. How you can write the formula you may use where we have resistance. Do I have anyone? You said the words like the same way I've been saying them. You tell me you write this, you say equals, you put this, you say this. I want that one person who can just repeat what I've said or what I've been saying. Okay, no one. Maybe don't want delays. Let me do it, and then maybe I give the third person the chance. So for this case, the thermometric properties are and not X. So if you're looking for the unknown temperature, you come and say that unknown temperature is theta. And of course, I'm obtaining it. So you say equal sign. Okay. Then after that, you'll be like, at least I'm sure that there is a division sign there. And then there is also times what? Times 100. And since I'm dealing with Celsius scale, the question we always communicate, things will be Celsius. So that means the final temperature will also be what? Celsius. Are we together? Like that. Then you'll be like, at least one thing I'm sure of, this part will be minus R naught, even this one will be minus R. Now, remember I said X naught, but X is a property and the properties are many, but it should be naught. Maybe one way you can recall, yeah? Remember I told you that, remember naught comes from 0. It means the value of the property at 0. That's why I told you that if at all you're seeing a chance of having something like 0 minus 3, if you can have 3 minus 0, you go with this, because this is going to create a negative that is going to give you a time. So look at it as something like that. That 0 is minus 0 minus X naught. The value of the property at what? At 0. So it is always better to have minus 0, not 0 minus. Maybe that one can also help you to recall that step. Then after that, you'll be like, what else is missing? You'll be like, I'm missing now R, theta, and also R at 100. Then you'll be like, of these ones, which one is going to be here on top, and which one is going to be down? Then I told you what to do. I told you what to do. Simple. Look at this theta and be like, it is theta equals, like theta is already on top. So it's R, even R at theta would want to be on top. Then maybe R at theta now R at 100 can now go down. You see? Something like that. Because it is very easy for you to mess up with the formula. And it is the same formula that is going to be working everywhere. Okay? So that is very important. Okay, now I've moved very fast. I want someone who is ready to raise up their hand. I want someone who is ready and can give me that formula for anything else. Raise up your hand, I ask. Yes. For me, I'm going to ask you for the constant. Okay, let me pick. Yes, Run Porters, unmute the constant volume gas
Yes,
thermometer.
good morning.
Morning.
Good morning, doctor.
Good morning. And we all know that
So
this
when
one,
it
because
comes
of
to
constant volume, you wait. Constant volume, what is the thermometric property?
I'm going to use, that is P.
P for pressure. Now tell us,
Yeah.
if at all there is that unknown temperature that we are looking for. How should we write?
So we are going to first of all mark it as theta, whereby we are going to say that theta is equal to.
It's equal to, what should I say?
Then we first of all draw that bar that is going to indicate that we are dividing. Yes, then we are going to, because obviously at the right hand side, we are always having the one of water. We are having our ice point, which is also the fixed ice point, which is P0.
So what should I
Up
write?
and then, so we are going to say minus P0 for up, and then down we also say minus P0. Yes, then because we are calculating the temperature, we are going to put times 100, then put it in brackets and place degrees Celsius outside. Then you say that the only debate we shall be having, if it is in an examination room, will be identifying which one goes up and which one goes down, of which
Of
the one
what
that
and
goes
what?
up that is P theta up,
P theta up,
and then P100 down.
P 100 down. Okay, that is good. That is good. So
Okay.
make sure you don't forget. The moment you realize that you're starting to forget, you simply try the derivation because you also did it. So this is just a way of trying to memorize. But if you have a better way, you can use your own way. So that is it. EMF, for the thermocouple, we use E. Constant pressure gas thermometer, we use the volume of a fixed mass of a gas, that is V. And we have all the expressions in the notes. So let's go through these things very fast. I remember trying to pinch the screen and giving you a chance to go through everything. So I believe as we read things here, they are going to just be making sense. So we are going to read through the steps of coming up with that scale. I think the notes are these ones. Setting up the Celsius temperature scale. Okay, so they are saying we are setting up Celsius. So when you see setting Celsius, you think of ice point and also the steam what? The steam point. Very important. The lesson is done. That's the formula we're going to be using in calculations. I give you your research work, you just go and enjoy. So first and foremost, choose the thermometer you're going to use. And also choose the thermometric property that you're going to really go for. And let that thermometric property be X. That's how the steps are supposed to be written. First, choose the thermometric what property of the substance and let it be X. Then you proceed and measure the value of the property at ice point and let it be X naught. Also measure it at steam point and let it be X what? 100. You can separate those steps or you write them at once and you attach the word what? Respectively. Hope you know how it is used. Are we together? Then after that, you measure the value of the thermometric property. I remember telling you that for the value, you will always measure it because you have the thermometer. So that one will always be obtained. But what you may not be in position to get is the temperature of this random tap water you got. That will be the problem. That's why even they are mentioning it clearly that it is the value at an unknown temperature theta and let the value be x theta. But even x theta, you know it. Yes, you know it as I told you. You can really get it if you've been following. Then after plot, and we agreed what are we plotting? We are plotting the value of the property against temperature. And we saw 0 goes with what? X naught. Theta goes with what? X theta. 100 goes with what? X 100. Then I told you how the slope is changing y over changing x. We applied the gradient, we simplified and made we made theta the subject. These are things we did already, okay? And then you can see what is common. Theta equals the division sign. You can see this minus x naught times 100. The answer shall be in degrees what? Celsius. Then what do we have on top? X theta. Why? It wants to be like the theta we are getting, which is also already on top. Then down you will have x what? 100. Theta on top. If at all that is hard for you, at least you help me and recall. You may not know the spelling of theta, but that is it. but theta begins with the T. You understand? Theta begins with the T, and T, you can write the word top. Okay, you understand? Theta, T, top, on top. So R theta on top, X theta on top, L theta on top. That is the only confusion. And 100 is down. 100 is down. 100 is what? Is down. Hope that has been understood. The person playing with our screen, please leave it. Now they are saying that the above equation you're seeing is the one that defines the what? The Celsius scale of temperature. That is it. And they are saying we can simply remove X and put other thermometric properties. And that is it. You all know that for the thermocouple, what is the thermometric property? EMF. So we are using E. So you can see theta equals times 100, answer is in degrees Celsius. You can see minus E naught minus E naught. E theta on top, E 100 down. Is that hard? Platinum resistance, this one we wrote it. Constant volume, this one we have just handled it. Liquid in glass, you know the thermometric properties, length of liquid column, which is L. Are we together? And also same thing, we are having the theta equals, we are having the times 100, we are having the degrees Celsius, we are having the minus L naught, we are having the theta on top, 100 down. Constant pressure, we all agreed it is volume. That is the property, of course, of a fixed mass of a what? A gas. You can also see this. These things are just. So when they give you a question, you know the formula to use, you just paste it there and then you get the answers those people want. Very cheap work. Very cheap work. Okay? Now, very fast Kelvin scale. Now, with Kelvin scale, things are a bit very weird and easy. So on top of being weird, they are very easy. So you all know that the Kelvin scale, we said, since the Celsius scale took the ice and steam points, for it is left with only one fixed point, and that is the triple point of water. It's the one that it uses. It's the one that it can use. Okay? And you all know that the triple point of water, you all know that the value is 273, and you all know it is 0.16. 1.5 is absolute zero. Okay? I believe people recall that at least. Now, how are you really going to do this? If I told you are in the lab, you want to come up with the Kelvin scale. So Kelvin scale, it's going to be a bit sensitive, but cheap. We shall be done with it, but you may look at it and be like, are we really done? Yes, we shall be done. So just assume, remember for it we said it begins from what? It begins from that. Isn't it what we said? And you all know that the triple point of water is this 16 kelvins, okay? Now we said that since this is the triple point of water, we can call it maybe T, temperature T, okay? Yeah, we can call it just T to mean triple point of water. Are we together? Now, after ensuring that that's the temperature you have, you come and get the value of the thermometric property. Remember, we have been using X. So you get the value of the thermometric property at that temperature, which is X what? XT. You can convert that one to degree, but no, we are dealing with strictly kelvins, okay? So you set this, someone may be like, the other time we are using ice, then we use the steam. We used the ice to get 0. We used steam to get 100. Now, what are we going to use to get the triple point of water? You go back to the definition. We say that the triple point, all the three states are coexisting at equilibrium. So you can do this in the lab. Yes, you can have a setup that is having all the three states coexisting at in equilibrium, then you notice the temperature that is in place. So that is very easy. Okay, so after having those conditions of temperature, you measure the value of the property, the thermometric property in place, and that is the XT. Is it okay? Then after that, for this case, we don't need the value at absolute 0. Remember, absolute 0 is not part of the fixed. It's not even a fixed point. Don't even mind it. The only fixed point we have for the Kelvin scale is this value of what? Triple point of water, nothing else. So after that, get your tap water, any water. I'm using water because that's one thing you can really never forget. So get any tap water. You don't know the temperature, and that temperature is theta. But since you're using a thermometer, you very well know. A thermometer having a thermometric property, you like it or not, you get the value of that thermometric property, and it will be x what? X theta, isn't it? And I remember telling you that values of the thermometric property, since you have the thermometer within your hand, these ones will always be known. That is known, this is known. The triple point of water is known. So the only unknown that we have for the Kelvin stuff is this theta. We don't know it. So here we are not going to apply anything like gradient. That's why I like it so much. Here gradient is not going to work. We are going to use something so simple, basic math. And what do I mean by basic math? Remember, we are looking for temperature, isn't it? We are looking for temperature. So you're going to say, if the triple point of water, this one, 273 point this kelvins, if at all it gave you, remember we are looking for what? Let me ask you something. We are looking for temperature. You know those things of mole concept, yeah? What we are looking for, is it supposed to, you know these things of mole concept where we say x reacts with this to give us this, like x equal to y. So we have this position, which I'm calling the left hand side, then this position, which I'm calling the right hand side. So I'm asking you people, that thing that we are always looking for, is it always on the right hand side or the left hand side? Like that thing we are always looking for, where do we always underline? Where do we always get the answer and underline? Is it on the right or the left? You help me with that. Then for me, I will help you with the physics. You tell me, where do you always put that thing you're looking for? Where do you always have your answer and where do you always underline? Where do you always underline? Yeah, I think people have it right. It is always on the right. Thank you so much. So since you all are aware that we are looking for the temperature, so I'm going to have the triple point the other side. So I'm going to be like, if this value of the thermometric property at the triple point of water came from the triple point of water, this. But that has been a by the way, before you can have your things the way you want to have them. Yeah, you can have your things the way you want. But me, I was preferring this because I'm looking for temperature. So I want the temperature to be on the right. So I be like, if the value of the thermometric property at the triple point of water came from the triple point of water, what of the value of the thermometric property at the unknown temperature theta? What is that temperature that gave us? What is that temperature? What is that temperature that gave us that value? So I'll come and say, I think you people know what happens. Do you people know what happens? People may say, what is that? You people, you all know that we say 1 kilogram is equal to 1000 grams. What of 5 kilograms? You all know that we say 5 times 1, 1000, isn't it? Over this one. Isn't it what we say? So it's what I'm going to do here. I'm going to say, so I'll get x, that one, theta, you understand? Times the 273, like that 160, okay? And then over the x, t, then I will have what? Degrees Celsius. Sorry, we are dealing with the Kelvin scale. I beg your pardon. The answer is supposed to be in what? In Kelvins. I don't know if I've left anyone behind, but that's the formula we are going to have. Even if you're supposed to write the steps in an exam, the steps will end with that formula. So as a mathematician, as a mathematical physician, you're supposed to now to rewrite that in a better way. You understand? You come and be like, so that is so you come and be like, the theta that we are really looking for, the temperature that gives you the value of x theta, it is that one. So you have x theta, then down you will have xt, then of course times what? This value, 16, then it is supposed to be in what? In kelvins, like that. You people, do you want to tell me that is hard? I'm going to pinch for you the screen and then you look at it and tell me whether we are good to go. Because now this is another temperature, but for the Kelvin scale, someone will be like, how do I really know it's the Kelvin scale? The question tells you. Yes, the questions will be very clear and you will know. And we are going to see some examples. Okay? You're dealing with the Kelvin scale where the only fixed point or pass is the triple point of water, with its value as 273.16 in kelvins. You understand? And you know for it begins from absolute zero. That's why they also call it the absolute scale. So first get the value of the thermometric property at the triple point of water. Then get any other thing at any unknown temperature that you know. Sorry, at any unknown temperature that you're not sure of. Get the value of the thermometric property. Now come and use basic math. If this one came from this, what of this? So if xt came from the t, the triple point of water, what of the x theta? Yavudemu theta, from which theta did it come? You understand? So that theta is that one. X theta over x theta times the other one. So if you're very technical, you can still see that x theta is on top. Just because this time round, down we're having xt, because it is a Kelvin scale and it's only the triple point of water that is there for us. Then we multiply by the triple point of water, then we have our answer in kelvins. So realize that this one, you may not be in position to cram it, but at least its derivation is very cheap. Yeah, you can easily derive it and bring it back to life very fast. Then you apply it and calculate. Yes, if xt came from triple point, where did x theta come from? It came from this, and that is theta. So equate theta to that. So people who are on, is the formula okay? Can you really later on read it and also try to come to come up with it on your own? Okay, 5 people have supported it, and that is good. If people are really following, that is good. So we can proceed. Okay, now the lesson is done. That's what I can say, and congratulations. I told you this is the part I'm concentrating on. The other part that is to do with thermometers, it is yours, and I'm going to give you the criteria of the research. You will not even need my lesson after. Yes, you will not even need my lesson after. Yeah, but I would want to first see something in here as presenting this work, so that I be like, yeah, people are really doing the needful. Okay, the lesson is not even yet 3 hours, but people ran away, because I believe we started when it is almost 10, but it's not even 1. That means it's not even 3 hours. We are just beginning the class. Okay, now we can now go to our book and see how the Kelvin scale can be established. Okay, so I'm going to come here and check. So they are saying steps to establish Kelvin scale. They are saying first select the thermometer and also be aware of the thermometric property we are using and let it be X. It being a Kelvin scale, we only have the triple point as our fixed point. It's the only one that is obvious. So we are supposed to measure the value of the property at triple point and let it be X theta. Then after we measure you understand, of that property at the unknown temperature. You all know what we do. Just get the thermometer, dip it in water. That's why I've been saying any water. Hope people understand. That unknown temperature, we agreed, let it be always what? Theta. And the property shall be X theta. So that unknown temperature we have been looking for, this is the what? This is the formula. I think you know how it comes about. Just basic math. If this is this, what of this? That thing is the unknown theta. Are we together? So people, that is it. And congratulations. You can see we are beginning with examples. Though there is this thing that will help you so much in scenarios. Yeah? The temperature scales may not agree in one way or the other for the different thermometers. So they are saying different thermometers will give you different readings when measuring temperature of the same body, except at fixed points. I want you to listen. Why those points are called fixed? I told you that you're supposed to understand the word fixed according to English. Like they are fixed. Even when you change a thermometer, they already fixed. It will be them always. But if it's not the fixed points, different thermometers will give you different readings. Why? The platinum resistance is using the thermometric property as resistance. The pyrometer is using the thermometric property as wavelength. The thermocouple is using the thermal property as EMF. Do you expect EMF, wavelength, and what did I say else? Do you expect resistance, wavelength, and EMF to change the same way with temperature? No. They will only agree at fixed points, simply because the different thermometric properties, the resistance for the platinum resistance thermometer, the EMF for the thermocouple, the wavelength for the pyrometer, they are different thermometric properties. Don't expect them to vary the same way with temperature. So if you're not at fixed points, they will give you different what? Different readings. That is just a simple statement. And I think it is very clear. Now, examples. You people, trust me, if you have been following even the first example, you can attempt. But I'm not going to really give you a time. I'm going to do everything for you. Now, just cause this is our first calculation, yeah, with the senior fives of this year, measurements and dimensions didn't have a lot of things. So I think I should brief you about how calculations are supposed to be done in physics. But I think I told it to, I think it was in the lesson of circular motion, which is a topic that is very far ahead. Okay, but I'm going to just brief you, but I've told you where it is. And that lesson, I think it is on YouTube. Yes, so you go and watch. You just look for the mode of calculations in physics. Oh, anywhere in science. So for now, I'm going to just brief you. Then I'll give it to you in details. But for now, you have it and listen carefully. Yeah? The mode of calculations we are going to be following is what they call the ESCA model of calculations. I even taught it in ionic equilibria in chemistry. But why would I really extend stuff? I mean, I don't usually extend stuff. Let me give you the ESCA model of calculations so that you have neat calculations. Yeah, this is an academy. Let us explain everything because we are going to calculate. So why would I really not give you the ESCA model of calculations? Because I think most of you are listening to or you're hearing of the ESCA model for the first time. Let me see those people in the chat who are hearing the ESCA model for the first time. Because without the ESCA model, you cannot have the correct calculation. Never. That is a lie. In Luganda, they say, Obera werimba. ESCA model of calculations. Let me see those who know the ESCA model of calculations. So all calculations we are going to be dealing with, especially you physics students. Yeah, because in each and every lesson, at least we shall calculate. So I will never repeat the ESCA model. I will always refer you to the thermometry class. And I will tell you, go towards the 2 hours of the lesson. That's when it was explained. But I've told you it's also in equilibria, one ionic equilibria. It's also in circular motion, that is physics near 6 work. Okay? But let's talk about it. At least you leave the class. You leave when at least you have something new that I at least I learned the ESCA model of calculations. Now let me split them. I tell you what E is, what S is, C and A. Okay? So we are having E. So the mode of calculations, I mean the flow. Someone may be like, what do they mean by model? I mean the flow. How should your calculations flow? Physics, chemistry, biology, especially applied part of math. Okay. Now E is the expression. So we expect the expression to come first. Okay? We should have the expression. Now, what is this expression? What do I mean? Expression is what you people call the formula. Some people call it the equation, things like that, but formula is more common. Okay? Now, you should know that this formula, the very first thing must be correct. Yes. Must be correct, specific, and neat. I'm going to explain all these. So after having your expression, please have the what? So that is E for S from ESCA. Have S. S is substitution. Substitution, that is really self-explanatory. Now by substitution, this one must be correct. You understand? Where you have R theta, put there R theta, not R 100. And neat. I'm going to talk about that neatness. It is very key. Okay, let me tell you this. Let me put the formula. Maybe I should use that of okay, we are going to be seeing everything as we progress. Okay, then C. This C is what they call computation. Okay, someone may be like, what do you mean by computation? What are we really computing? With computation, here we are meaning the evidence of working. Yes, evidence of working. Some of you just copy. Now, the evidence of working is not necessary everywhere. There are numbers you look at and for sure you don't really need to show the evidence of working when the calculator can just do it. So I will add on and say that this one is only if necessary. So there is when the C will be skipped. But there are certain numbers where it is so important and it really makes your calculation easier. Okay? That is with if really necessary. You understand? If not necessary, please, you leave. Then A. This one is obvious. Of course, the calculation should end with what? The answer. Now, this answer is a wiseacre. It has three things you're supposed to really concentrate on. The very first one is the number of decimal places. Number of decimal places. Okay? Now, this number of decimal places, you can really do what you want, but I always advise members, if at all BPs, let me tell you that the standard that can really put you on the safest side is having a minimum of 3 DPs. But here I'm doing this in physics. Have it in mind that in applied math, the applied part of math, the minimum is 4. That's why when you check our lessons of applied math, we use 5 decimal places to secure our future. Okay? But here, minimum 3. Don't try too much for physics, chemistry, and math, the pure part. Okay? But there are things which I'll keep briefing you as we revise it. As of now, we just want to get the concepts and have all the concepts. Okay? Then the other thing concerning the DPs, look at the question. Yeah. Especially these ones of thermometry. They are going to show you a thermometer giving values at 1 dp. Then also have your answer to 1 dp. Don't waste time. They have given you a value of temperature to 2 dps. You also have it to 2 dps. So you can always look at the question and look at which values does the question have. Those values, which dps do they have? If the dps are not common, maybe there is a value with 1 dp, another one with 2 dps, another one 3 dps, also choose the dps you want. Excuse me. But if at all the question has not specified, it is just use 3. Just use 2 dps. So I've not said that when you use 2 dps, they will cancel your work. They will mark. But then there are things you're supposed to be knowing. That angles in mechanics 2 dps, angles in physics 2 dps. Okay, things like that. If at all, provided you're part of us, there is no way all those things will give you a time. I just have that fear that students always do the opposite. It's my fear. That's why I always want to make the point strong and drive it more to home so that people never forget or take it for granted. After doing this answer is a WYSEC and it's having 3 choices. The other choice is standard form. Okay? It is better to have your answer in standard form if possible. If people don't force standard form, yeah? Don't force standard form. If possible and if you really see it necessary. Okay? There are some numbers. If at all you get your answer like 5, you leave it as 5. Don't say that doctor told us that standard form, then you come and say smart 5 power 0. Yes, it is 5, but now for you, you're overdoing it. That's not what I said. Okay? So that one is not advisable. So for standard form, I think I'll need to do this and tell you that if you have 5 and you try to make it 5 because we said standard form, this is not wise. They may mark your work, but someone may even think it's a different value. If they mark 100 students having 5, if for you come with 5 times 10 power 0, they may even see it as 100 and you fail. So what I really mean here is having a value like maybe 0.005, okay? Then you decide to make it 5 exponent negative 3. This is what I mean by standard form. That is very nice. But even when you leave it as this, it is okay. But it is just better. It shows that you really know the SK mode of calculations and you're doing everything needfully. Okay? Then the other last one are the units. Okay? Let me tell you, this point is serious, the point of the answer. Because even the units, they have 3 choices. Yes. On top of the answer having 3 points, even the units have 3 points. Yeah, there are those units that are known. Those ones are known. Those ones we call them SI units. And we talked about those in the lesson of dimension. I don't want to waste time. So there are those that they call SI what? SI units. Okay. Then there are those that are derived. Yes, there are those we shall always derive from the equation. Yeah? We shall see those in some future topics derived from question. Okay, then there are those quantities that have no units. You know those things. Okay, someone may be like, what are those that don't have units? We have relative density, we have refractive index. Yeah, but we shall see all these things in the future. We shall apply all of them. Then the SI units, those ones you know. Resistance is ohms. Velocity is meters per second. You know those things. So that is it. So you really need to take a screenshot of that SK model. It is so important. Yeah. So about the substitution where I said it must be clean, I'm going to be showing you as we calculate. Okay? I'm going to be showing you as we calculate. But maybe to show you something about substitution. Just something small. Because people usually WYSEC, and this is the mistake that is mostly done by students. If at all you come and write your formula, and then you be like, which thing are you really well conversant with? Okay, let me use speed, distance, and time. Maybe you know that maybe speed, okay, speed, which is V, speed is V, and distance is S. I told you that in linear motion over time, okay? And maybe they have provided you with, now this is the expression. So this is expression. So when I say that it should be correct and neat, it is correct and neat. When I say neat, that means I don't want you to add there things that are not there. People have that tendency. You understand? It should be correct it should be correct. If this is S, write S, not D. If this is small t, write small t, not capital T. This is physics, not applied math. Use notations the way they are in textbooks. Okay. Now let's say that you have been provided with velocities 2, and then maybe you're looking for S, and maybe they have provided you with time 5 seconds. This is what most of you do. Most of you come and do like this. You say over 1 because you want to cross multiply. Now this one is wrong. The moment I see it in your work, I cross it. In holiday, we shall have 9 exams. You will see. I will cross your work. I will not mark it. For me, I take that one as being tidy. You don't need. The moment I see that, the moment I see these things of cross multiplying, these ones, you're not neat. You're not neat at all. So what do I really expect? I just expect you to just have something from such a step. You simply say 2 is S over what? Over 5. That is it. So for such an example, you don't even need to show the evidence of working, so no need of computation. You can just straight away go to the answer and say, S is 10. Then the unit meters, everyone knows that. So no need of writing 10 in standard form. Only write standard form where you need it. Even when you get your answer 0.5, 0.5 is okay. You can leave it like that. Even if you don't go to the exponent, negative 1. But there are those values you get with 0. What. So many values. Yes, those ones you can really go for the standard what? Standard form. And I taught you how to write it in the lesson of measurements. So people try to get what I mean by not being neat as you substitute. Just leave the substitution and let it be in line. Let it be in line. Some of you also do this. They have provided you with you're doing force. At least all of you know that. I'm trying to look for the expressions. You all know that force is MA. Hope that is right. So they give you mass that is maybe 2 kilograms. Remember, it's supposed to be in kilograms, and maybe acceleration that is 3 meters per square second. So you write your formula like that, which is correct. Then you come and substitute, then you say F, because you know 2 times 3 the same as 3 times 2, you come and say 3 times 2. For me, when I see this work, for me, I cross it. Why? Because it's like you're telling me M is 3 kilograms, yet it is 2. But for you think because multiplication is commutative, you can do what you want. So for me, I take this one as wrong substitution. So I don't proceed with marking your work, I just cross it. I don't know whether people are trying to get. So as you're substituting, be neat. Let things be in line. Don't introduce things that are not there. Things of cross multiplying, things of saying over 1, those things don't exist. Where you need to show evidence of working, especially where quadratic equations come in, show. Where they don't come in and you don't need those things, don't show them. Just move from expression to substitution to answer, and that's what happens in most of the cases in physics. Yes, in physics, in most of the cases, is formula like that. Formula over expression, you substitute answer like that. Because there is a tendency of deriving things and making what we always need the subject. So you have the perfect formula for the perfect calculations that are going to come. Hope we are together. Okay, so that is about the ESCA model. So as we are calculating, I don't want you to do anything that is not part of this. Okay? Now, I think now we can do some examples. Yeah? You can see that's what defines an academy. People thought thermometry they are being or they are finding issues with calculations, and they are the ones we are to begin with exactly, but that's not the case. You see, in the future, we are going to be revising all these things. But I'll be referring you to come here first, because it is only those who will have given this lesson time that will understand now the scenarios to do with thermometry. Okay? So this first lesson, the moment you hear that I'm introducing a topic, if you cannot be patient, don't come. because every statement I'll read, a word I'll read, and I will just get a thought that a student out there that would want to know more, I will speak because I have the content, so I will speak. Okay, now examples, very cheap. Now the other thing I may add on, before you even write your expression, you can have a summary if you want. Yes, you can have a summary of the question if you want. Yes, so I'm going to come here and say summary of the question. So this one is not compulsory. Yes, it's not compulsory. You can have it or you can leave it, but it can always guide you. So for the first example, maybe I can have the summary so that I show people what I mean by a summary. Then maybe I can skip it for the next example so that people can maybe weigh the two and pick on what may really work for them. So for this example, I'm going to have a summary. Then for the other one, I'm not going to have a summary. Okay, so what are they saying? They are saying that this is how questions come. So we are applying whatever we have been gossiping about. A resistance thermometer, so expect values of resistance. Has this resistance at ice point. So that is R0 or R0. Okay? Are we together? So I'm going to come and say R0. So I come here and say summary before even the expression. So I come and say, sorry, R0. What have they said? They have said R0 is 21.42. So it is 21.42 and the unit is ohm, okay, or ohms whatsoever. Then they are saying that at steam point it is 29.10, but that is steam point, so that is R100, okay? So I come and say R100 is 29.10. Do you see they are giving you their values to 2 dPs? You can use commas, even if you don't use slashes. You can use commas, you can use slashes. It is just a summary, not compulsory. So they cannot penalize you for the design you put. So they are saying that they also had this value at an unknown temperature, theta. So for this question, they have given you theta as the unknown temperature. If they don't say, or if they don't mention it that theta, please, you're supposed to say let the unknown temperature be theta. They can make it T. So when they make it T, you're supposed to adjust that in the expressions you have been writing, wherever there is theta, you put there T. If they change and it is capital T, do the same. Even if they make it alpha, wherever there is theta in our general expression, you put there alpha. Simple. Okay? Now they are saying calculate the theta on this scale. So someone may be like, how do I know the scale? Is it really Celsius or Kelvin? The moment you see ice and steam point, that is Celsius. When you see only triple point of water, that is Kelvin. So you know which formula to use. Okay? So they are giving you R theta as 28.11 and they need theta. So you come and conclude the summary. And so that I've also been provided with R theta, which is 28.11 this, and then they are looking for theta. So I'll say theta equals question mark. Do you see that? That's what I meant by the summary. So after having the summary, it can really guide you. It can make your substitution so nice that you don't have to go back and read the question. You just refer to it. But you can also make the summary in the question, because in most of the cases, you don't hand in the question papers. You leave them in the examination room. So you can make them dirty anyhowly. So you come and be like, this formula was taught. So you be like escamodo. Escamodo expression. Now you come and write expression. So you all know there is a division sign. This, okay. I also don't know the formula. I just derive it slowly. Then I know that here I will have R0. Even here I will have R0. Then of course this will be times 100. Then we agreed that since we are getting theta, R theta on top, and also you have other reasons, then R 100 down like that. Then I know whatever I'm going to be getting shall be degrees Celsius. Okay? So I can even, you can decide to just have it like that. But if you want to have the unit, it is okay. If you want to add there degrees Celsius, it is okay. Yeah, it is okay. But if you want to show at once, if you put it here, it is okay like that, because even the 100 is degrees Celsius, okay? But if at all you also want to put this in brackets and also say that I'll be getting my answer in degrees Celsius, it is also okay. If at all you don't put the unit and put it on the final answer, it is also what? Okay. Remember, it is not a must for a unit to appear in the expression. Yes, a unit must come the final answer. The expression should just be correct, so you can just have it like that. Very correct. Then you'll be like, Escamodo, expression done, so I'm supposed to substitute. So you come. R theta, where is it? 2811. R 0, where is it? It is there, 2, 1. You see the importance of a summary? You don't need to go back. Yes, and you read the question. R 100, it is 29.10. Then this one is the same, 2142. I don't even look up. Then times this. Now this is what they call the substitution. Clean. Don't add anything. Don't add anything. Some of you end up skipping it. Never skip. The substitution should be very clear so that someone is like, oh, this one is the R theta. Oh, this one is the R naught. Oh, this is the R 100. You understand? But some of you have a tendency, you press the calculator, and instead of having all this, for you just put the value from the calculator. You're missing out marks for substitution. So always substitute well so that someone can really connect the expression to the substitution. Someone can be like, oh, this one is this, oh, this one is this. Someone marking you be like, yeah, this kid really knows what they are doing. Now, there is what they call evidence of computation or evidence of working your computation. So you look at that step where we are. Can you put that thing in the calculator at once and get the answer? Or you really need to do things bit by bit? That's where the examiners get you. There are students who have issues with pressing the calculator. For you, I advise you, please, you can first do things slowly. Are we together? You come and say, for me, I'm not going to risk. But if you're that student who can really see what you're supposed to do here, do it and just put your answer. They will mark your work. But me, I will just come and say 28.11. I'm using my calculator currently. Minus 21. So I need someone to also be pressing so that I don't give a wrong value. So on top, for me, I'm getting 6 point. Especially when the evidence of working does not overchange the values. You can have it out of. Then down I also come and say 29.11. Sorry, 10. Please make sure I get right values. I need to have a counterpart helping me with this. Then down I'm getting 7.68. Hope that's what everyone is having. Time was 100. So if the examiner said that if someone shows the computational evidence of working, give them a score, you get this score. But if you don't show the score, they may end up putting for you 2 marks here or 2 marks on the answer. Because you people, you can put that thing in the calculator at once. How do you do it? You use brackets. So those who want to put it at once, open brackets, put in that, close brackets. Then when you reach here, use the division sign. It is okay. If you don't want to use the division sign, there is a sign you can use. I don't know whether I should also show that to people, but I think I showed you that in the lesson of measurements. Yeah, but there is that button. Let me show it to people. Yeah, really, this is an academy. Every chance I get to show you something that is really going to benefit you, we should really use that chance and not take anything for granted. So that is my calculator on screen. So the button I'm meaning is this. Are you seeing this button? That one. Are you seeing that button that has a mixed fraction? Yeah? AB over C. Very important. Yeah. So that one is, you can also use it for division. Yeah. So instead of using this, you can use that one. It will bring something like this. Then you also put this in brackets. Then after that, you set time was 100. You get the answer at once. But if you believe that is too much work for you, follow the SCAM model peacefully. After the substitution, I'll try to come and show the evidence of working. Now, don't you see that what you have is easily pressed in the calculator and you can really come up with the final answer of theta? Okay, and when I say 6.69 divided by 7.68 times 100, I'm getting 87. I can decide to have my answer to 2 dPs. I can be like, this is temperature. You can use 1 dP, whatever you want. Yes, whatever you want. Whatever you want. I don't know which, how many dPs do people want? How many should we use? I'm getting 87.11. Is it what people have? 87.11. Now, this one does not need standard form. Why would you even have standard form on such an answer? So standard form is out. dPs you have chosen 2. The unit you're dealing with temperature and the scale is Celsius. So the answer, the unit should be degrees what? Celsius. Why I really want you to be serious with the SCAM model, because there are questions that will award the value and the unit separately, whether I have score or full marks. But please, the value and the unit are so important. They make up a complete answer. So when you have such a solution, no one can say you're very disorganized. Let me tell you, all scholars at SSA should have such calculations. And I know those who have been following us well have such work. Have a summary to guide you. Have the expression that is correct. Have a substitution that is correct and neat. Don't skip. After the substitution, you can do all the kind of evidence you want. Then after, have the answer. Standard form if applicable. dPs minimum 3. Someone may be like, but doctor, you said 3 and we've used 2. Because I had 109. Why won't we have just 1? But trust me, even 109, they will mark your work. Yes. Trust me, even someone who would say 87.1, they will mark your work. The problem is with 87. Whole numbers are very risky. So have it in mind, and maybe I should have it as a note. If the calculator does not give you a whole number, avoid it. Yes, please avoid whole numbers. Let me put it even in red. You know, for us who did color psychology, we know that red means danger. Okay? Avoid whole numbers unless given by the avoid all numbers unless on calc. If they're on the calculator and the calculator is the one that has given you the answer as 5, okay. But if the calculator gives you 5.001, don't say those zeros are many. Please write that answer. That's what they want. So whole numbers are overrated in science. Have that in mind. Hey. So I think that has been clear and the point has been taken home. I think all of us should have a summary. Hey, all of us should have a summary, because the other method may really make some of you big-headed, which I don't want. So let's look at this number. It's also a number to do with resistance. And let me tell you, you're going to tell me to leave it. You're going to tell me it is doable. Let me tell you, you're going to tell me it is doable. Let's read it. They are saying the resistance of a wire is measured at ice point, steam point, and at unknown temperature, what? Theta. Okay? And the values are these ones. So this value, they are saying respectively. So this is a value for ice point. This is a value for steam point. and this is the value for theta. Okay, so the summary I meant that if you want to avoid it, you come to this question, the very question below this value or on top of it, you be like, if this is ice point, then this is R0. Then if this is steam point, this is R100. If this one is the one at theta, then this one is R theta. You get it? Like you just attach those values on the question. So if you're running out of time, you can have your summary in the question by attaching those values either on top or down, depending on where the space is. Is it okay? Then, you people, do I really need to do that number? Don't you see it is the same as number 1? Is it okay to label this number as assignment? Do you see why I always want us to give concepts time? Because trust me, if you just bump into these terms of ice point, resistance, theta, you just see things as really weird. And you just have a feeling that numbers are different, yet they are the same. Is it okay? Should I label that as assignment? Okay, I think I'm having some 5 people supporting me. And thank you for the support. I don't take that for granted. Okay? Assignment, that one. So I'll be happy when I see someone doing work according to the SCA model. Very organized. I will not take that for granted. Okay? People, let me hope the screen is very clear and we don't have any issues. The voice is okay? Yeah, because these are national classes. So we need to be sensitive. Okay, where are we? Let's look at number 3. Let's look at number 3 and see. Okay. They are saying, why is it having ticks? Seems I used it in one of the previous illustrations. Okay, that's the number. They are saying that the length of the Machulet column is this at ice point. So this is length. So we are using L. So it's supposed to be neat. So you come as a scholar of science. Okay? You come down and say, now you attempted number 1 very neatly. The examiners have no problem with you. And then you're supposed to come and let's first secure our worker document. Okay. So you come here and be like, I'm supposed to do question 2. Okay, let me say question 3. Let me follow the order. Then you be like, they said length at ice point. And what was it? So you say length at ice point, that is L naught. Okay, so you say L naught. It is 2 centimeters. But you see, they are saying 2.00, but that is not important. Even in the first question, they had said 29.10, but that last 0, I would ignore it. But I left it for that number, and I wanted to tell you maybe on this number that for this one of length, that 00, you can leave it. Hey, you can just say 2 centimeters. Yeah. After all, the decimal places are needed for the final answer. And it is the same thing. You have not changed the question. Hey. Then 2.73 at steam point. Steam point is length at steam point is L100, isn't it? And it is 2.73. So I'll come and say that at steam point that is L100. And this is 2.7 what? 73 centimeters. Okay. Where are we? They are saying what temperature on the mercury in glass thermometer. So remember, the thermometers are called liquid in glass. And we said the liquids can be that highly toxic called mercury. It can be the ethanol. It can be water. So this time around, we are having mercury as the liquid in glass thermometer. So they are saying they need the temperature that corresponds to this. Are you seeing that for this case, they have not specified the temperature? So you're supposed to tell the examiner that you're letting the unknown temperature, because they're asking for it, you're supposed to let it to be theta. Before you even call this one L theta, that is the mistake students do. They mark their work. But when I find it as Paul tutor, I will not mark it. That's why in most of the cases, students don't allow me to mark their work. They tell me you let the consultations help line markers. Because for me, I look for perfection. If I don't see perfection in your work, okay, I be looking for mistakes because I believe mistakes are supposed to be part of a student's work for the whole of senior 5, even in senior 6. Okay, so you're supposed to at least first come and say that let the unknown temperature, and you let it because it is not in the question. You're the one bringing in your bogus. So you're supposed to defend that bogus as you're using it in the answer. So you say that let the unknown temperature. Unknown is enough because it is like the question has a certain temperature that is unknown and you're letting it to be theta. So you come and say that let the unknown temperature be the theta. After telling them that, now come and tell them that the L at that unknown temperature theta is the one in question. And what is there? We are having, where is it? It is 8 point, are you seeing it here? 8.43. Oh, are we together? It is 8.43. It is centimeters. Okay? Yeah. And the mere fact you've said unknown, now everyone knows that's what they are looking for. And then now this one, yeah, this one is cheap. I'm going to come and say, my theta. You people, you know the story. I put here a line. Okay. I know in the end it will be times what? Times 100. Are we together? Then I know, since it is L this time round, I know it is minus L not, even here minus L not. Then I know because of theta will be on top. Then 100 will have to come down. No option. You understand? Very, very cheap work. Very cheap work. But then as you really progress, remember you'll be having it in mind. So you'll be like, this one is supposed to be L theta minus here always L naught. Then L 100 goes down. Okay. Then L naught in times that one. Then as Paul Duter, when I see that, a very neat expression, I'll give you a score with 1 heart. Then you come and put a bar. Yes, if you want to utilize space. Okay. Then you come and say, now I'm supposed to have a very clean substitution in my expression. So you come, most of you do this other mistake. You come and put here equal sign. And I know all of you are on right now, do that. You put here equal signs. When you put here equal signs, you've left this theta behind. When you leave that theta behind, then what are you doing? Are you getting the, okay, are you equating space to our work? So you're supposed to make sure that the substitution resembles the expression in the name of replacement. That L theta is being replaced with something like that. What doesn't have replacement, it must come back. Theta is what we are looking for, and meanwhile, it doesn't have any replacement. You're supposed to bring it back. L theta, where is it? It is the 8 point minus. Are we together? L naught, what do you have? You're having 2. Out of, what do you have? L 100, 2.73. Minus L naught, what do you have? You're having 2. Times 100. When I see that work, and I really compare and I don't see any other untidy things, funny things you've added, I assure I'll give you that tick. You see? Then I'll have the final answer. For this case, I'm not going to have the evidence of working. I'm going to use the other formula I gave you. I'm going to go to my calculator. I'm going to just say these words because the other time I wrote them. I will open brackets and I've opened them. I'm opening these brackets with someone. Then I'll say 8.43. Then I'll say minus 2. I'll close brackets. Then I say divided by, I open brackets again, 2.73 minus 2. I close them again. Then I multiply by 100. And I'm getting 880. Do I have anyone with that value? 880? 880. You're supposed to just put the answer you get, even if it is big. But you cannot get a billion of temperature. That is too much. So for me, I'm getting 880. And the values in question are to 2 decimal places. And the other value I have, it is 8219. So I can have it as 82, but I can also have it as 1dp. They will mark. The problem is whole numbers. If the calculator has provided decimals, someone can be like, let me stop here. After all, 2-1 is the same as 2. Someone can stop there or put a 2. But me, I'm a fan of 2dps, 3dps like that. But to cater for whatever students will encounter as they progress in the subject, I will have it as 1dp. Then I'll put degrees Celsius. Then from here I'll mark your value if it is correct, and I'll mark your unit. I don't know whether I'm not really confusing you all when I say the minimum is 3 and it is the standard. That is to be on the surface side. But I gave you the general ESCA model, especially mechanics. My dear, when I reach mechanics, I will not even use 1dp. That one I use 3dps. Just because I'm looking at temperature as being something. But remember, we even said that these thermometers should be in position to even notice the smallest changes in temperature. That's why your 3dps are okay. 2dps are okay. 1dp is just risky. 0dp is wrong if the calculator has given you some dps. Are we together? So that is how cheap these things are. This is how work becomes easy with the summary. You just don't go back to the question. So failure of proper interpretation of the question is a wrong summary leading to a wrong substitution. So we'll only leave with marks for the expression, which is very bad. Okay? So let me hope we are together and I've not left anyone behind so far. Okay? Okay, let's see. What do we have? There is this. Yeah, there is this question. High yield for scenarios. What are they saying? They are saying when the above temperature is measured on a gas thermometer. Remember, for us, we got 880. So they are saying that when they measure it on a gas thermometer, remember ours was the one of mercury in glass thermometer. So they are changing the thermometer. They are saying that the value changes and it becomes this. So the point is easy. The temperature at which we are measuring, it's not a fixed point. Yes, and we agreed for a fixed point, things will change. Because here it is a gas thermometer. Whichever of whether pressure, whether volume, we don't know, because here they didn't specify which kind of thermometer, whether constant volume, whether constant pressure. But if it is constant volume, that means the way the pressure is going to vary with temperature is not the same way the length of the mercury column will vary. Isn't it what we said the other time? So you simply say it is simply because the length of the mercury column varies differently from the way pressure of a fixed mass of a gas varies with temperature. Do you get? The way length of the mercury column varies with temperature is not the same way the pressure or the volume of a fixed mass of a gas will vary with it. So don't expect to have a similar value at a point that is not fixed. The agreement shall only happen where points are fixed. Okay, this is now repetition. These are cheap things. Now, I want you to look at this number. You tell me if I should read, if I should do it, or I give it to you as assignment. You see, they are giving us 2 thermometers. Okay, yeah. So these questions are 2. Though they try to combine them and try to make things worse. You know, the wise aching of us scientists. So this is one question. Why am I calling it one question? It is a resistance thermometer. Then this one is another question. Why? It is a constant volume gas thermometer. So we expect changes in pressure. That's why you're also seeing that. Now, They are giving you different points. I want you to look at this clearly. They are saying that this 30 ohms is at ice point, so that is R0. I'm just hoping you interpret. When you tell me it is doable, I label it as assignment. When you tell me to do, we are going to do. Okay? We go. Then this one is at steam point. So you label this as, so this time around I have the space on top here. So this one is R100. Then they are saying that this is what they measure when they immerse it in a boiling liquid. You people, they have said liquid, not water. We know that water boils at 100. So it's like the question will have no unknown because they will have provided each resistance with the corresponding temperature. But here they have just said boiling liquid. We don't know the liquid. That's why even the question is telling us to calculate the temperature at which the liquid is boiling. We don't know the liquid, we don't know the temperature. So somewhere you're supposed to write and select the unknown temperature, even if you don't set the temperature of the boiling liquid. What they tell you to calculate is unknown. So you're supposed to tell them theta. But if you're disciplined, you want to just be perfect, especially the SDAs, you say that let the temperature of the boiling liquid be theta. It is okay. But if you just want to be smart, just say let the unknown temperature be theta, period. Okay? Then they have provided this resistance as the resistance at that unknown temperature theta. So it is the R theta. So that's making the summary in the question. It is also easy when you substitute, you just look for them because you've used the arrows, so you can easily have that work. I usually use arrows in my explanations, and I tell my friends who are doing UNEB examination and assessment, I tell them that when you see work of students having a lot of arrows in question interpretation for those of old curriculum, I tell them that is my student. Because we handle so many students across the country. So I usually identify them with how they do their work because it is always really unique. Okay. Now, we went for another thermometer, the constant volume. So this time around, they are provided pressures. Hope you know why it is pressure for the constant volume. Now, we are going to come. They have said for the same temperature, so we are having these pressures for the same temperature. That is very key. High yield, same temperature. That means this one is for ice point, so it is P naught. This one is for steam point, so it is P100. Then this one is for the unknown temperature, the same order respectively. So this one is the P theta. Okay, now what are these people saying? They want you to calculate theta using the R's because they are saying Roman 1 for the resistance thermometer. So they want you to get theta using the R's. Then they want you to get theta using the gas thermometer. That means they want you to get the theta using the P's. That means here, since it is gas thermometer and they are P's, you know the formula to use. Yes, you just tell them, for you know that this one is going to be P theta and this one is always P0. Then you know that this one is what? P100. And then this one is always minus P0 times 100. And you know the final answer is supposed to be degrees Celsius. Why? You considered both ice and steam points for the scale. Are we together? Then for the resistance thermometer, you also tell them that I just can't prove it, but I know that if you need theta for the resistance, I know the formula. I know this is supposed to be R theta, R naught. You all note down R100. Again here R naught, then times 100. And then I get the theta, the unknown temperature. You people, you tell me, do I really need to do that question? Do you see that these people are just really playing on our minds? They just got two different questions and mixed them up just to make the revision really intensive. But I just needed to do only one number, then you do the rest. Should I label it as assignment or you really want me to do it? With that interpretation, it is doable. Leave it as assignment. Okay. the problem I find with students, they are good at deciding what I should label as assignment, but the problem is you guys really doing the assignment. People don't always do them. They be like, after all, I've understood. You people, you're not understanding. You're simply appreciating the flow of content. If at all I call people here and tell them, anyone, I tell them define thermometric properties, you can't. But all you can recall that everything that was said by doctor about it was very clear. That's all you can recall. Very bad. Okay? Now, examples on the triple point. Now, this one is the cheapest time wastage. I'm doing number 1, then maybe you do number 2. Then we do these last ones. These last ones are just fun, then assignment, and we shall be done. So in just a few minutes, we are going to have left this place. Yeah, we are going to be off the place. Okay, now this is about triple point. And we say triple point, when you see triple point, it can be in the same statement or same sentence as Kelvin scale. Yeah, they are just like this. They are just like this. Triple point of water, Kelvin scale, they are just together. Okay, now, what is the formula of the Kelvin scale? Because it is to do with triple point of water. That formula is easy to remember. I'm telling you facts, especially if you know that on top you're supposed to have x theta, then down, of course, you're dealing with triple point, so you need the value of the property of triple point. And this time around, because of triple point of water, you're multiplying by the value of the triple point of what? Of water. And what you're obtaining is always that value of theta. Okay? And the answer is always in kelvins. Do you people see that? Is that really hard? But remember, I taught you how to do what? To derive it, and I don't want to repeat myself. Yeah? I always endeavor to give every chance that I get to explain a concept my best, so that when it comes back, I don't really strain myself. So let's see those examples on triple point or the Kelvin scale. So you can have a summary. For me personally, I like that summary. If I have the time, I used to do them. I used to do neat work because I had very good sources. So I used to have neat work, the only neat work in a district. And on national level, I got maximum marks, maximum grades, maximum subject grades, maximum paper grades. They're saying that the pressure recorded by a constant volume thermometer at a Kelvin temperature. This is what I meant, that questions will always really say it. If they don't see Kelvin, you see somewhere triple point of water, you just know that the formula is changing. Physics is going to get tough. Each and every lesson will have a formula. But if at least you have the roots that can help you derive it and bring it back to life, you will not have the same pressure as someone who is just cramming them. For you be like, at least I can go somewhere, and you understand. At least you can sit down and derive these things and you get them back to life. You can really confirm whether they are right or not. So always make sure that as you're praying to God, you pray that you can really bring things back to life the way we bring them in lessons. Okay? Now they are saying that pressure recorded by a constant volume thermometer, of course, you know that when they say constant volume gas thermometer, the thermometric property is pressure of the fixed mass of the gases. So they are saying at Kelvin temperature T is this. Do you understand? Now what they have provided is the pressure at T. Now there is someone who is used to theta. Please, if you're used to theta, please be careful. Sometimes they can use capital T, sometimes they can use small t. So you should be that person who can remove theta and put t. Okay, you can first use theta. For you, if you're obsessed with theta and they have used any other letter, maybe k, first write theta in your side work. But as you're transferring work, remove theta and put k, remove theta and put k. It is the same thing. It is just art and design. It now turns from physics to art and design. Remove theta, put K. Remove theta, put Q. Things like that. So that is PT, like pressure at the unknown temperature T, and the question has mentioned it, so don't say anything. So in your summary, just come and say PT is this one. It is 4.8 exponent 4. Okay, so I'm going to come and say that PT, they are giving me 4.8, and they are saying it is exponent 4 pascals, though they are saying Newton per square meters, but I told you they are the same. You can use slashes, you can use commas, let me use semicolons this time round. Anything that you want. You know what you're doing, so be proud. Okay? They are saying calculate T. Before you even proceed, you come and write that. You say come and say, they are saying calculate T. So you write T equals, you put question mark. Then you also come, you put the semicolon again. You go back. If the pressure at the triple point of water is that, we agreed that triple point of water, we are going to be using small t. Now, what if the question gives you small t as the unknown temperature? Now, for you, change from small t to capital T for triple point. I don't know whether you're getting. Triple point, we agreed to use small t. This question, by God's grace, it has used capital T for the unknown. But what if it brings small t as the unknown? Now, for you, use capital. You understand? Since they used yours, use them. Yeah, tit for tat. So they are giving you the pressure at the triple point of water, like that. And what is it? They are giving it to you as 4.2 exponent 4. So it is 4.2. So I will come and say 4.2. This is exponent 4. And they are pascals or Newton per square meters. And they are looking for T. So for you who knows theta, for you used to this one, you know that theta is x theta. Even me, I'm used to theta. Yeah, so don't think you are alone, even me. So you just write, you first write that, and you be like, oh, so they need the t this time round, not theta. So you also come and say t. Yes. After that, you be like, they need now pt on top. This is how I'm relating things over, then down, it is the triple point stuff. Then we multiply by, be like, hey, but is it really 100? I thought for triple point it is the other value. You recall, you be like, oh, then you come and put it 7316. For me, if I see that, I just know the student. The summary alone can show. Those days I used to mark summaries in training just to make sure that students really have the summaries because they are just nice. So when you have this, I give you your mark. Yes, because why not? Then you substitute and get the answer. Now you're going to see that all the next questions are just easy. Just easy. Okay, so we are going to come here and say, okay, now that T, the one we are looking for, P capital T is this one, 4.8. Okay, exponent 4. Then down, we're having the 4.2, and it is also exponent 4. Sorry if I said any other value, then time was this. Okay, so you press your calculators and tell me. This time around, I'm not the one pressing. I don't know if really people are still with me. It's coming to 2 and some people have already switched off. Will you really manage classes of Science Scholars Academy? Because for us, we teach until the target is hit. Yes. Now, when you look at something like this, you don't really need to show us the evidence of working. This one is not needed. You can just press it in the calculator unless you just want to bring yourself issues. And let me tell you, if you're a student who knows math, there are things you're supposed to look at, obviously. You realize that this one will cancel with this. So when you're pressing your calculator, just say 4.8 divided by 4.2 times 273.16. Do you see that? Is that really hard? 10 power 4 is cancelling. So just get 4.8 divided by 4.2, get the answer. You just need to understand that since I'm dealing with the Kelvin scale, in the end, my answer is supposed to be in Kelvins. If standard form is possible, I have it. If it's not possible, I leave it. If the DPs come through, well and good. If they don't come through, I leave them. So I need to see the answer in the chat. Yeah, someone has an answer to 3 DPs and I've liked it. I think let me also have it like that. But Kelvin, since even the triple point of water is given to 2 DPs, let's have our answer to 2 DPs. Because I told you when the question communicates, please, you can go with the question. So let's stop on 1.8. Yeah, not forgetting the Kelvins. So Kelvins, you're supposed to understand that it is capital K. You see, physics is not like math. You see, for math, if a student tells me that, doctor, we need to do so many examples, I may buy your idea. But physics, no. I just believe if a student knows the concept, I believe they can play around with it. And if they can play around with the concept, I believe they can really make it. So with physics, I don't really buy the idea of students who tell me to do a lot of numbers for them. I don't. Let's look at this theory. We see, example 2, we see if it's really doable. If it is doable, we shall see what we can do next. So they are saying the resistance of a triple wire at the triple point of water. What have I said? Did I say triple wire? It is platinum wire. I don't know, right? But I'm not tired. I cannot say that. I'm not tired. So they are saying that the triple point of water, this one is known to 7. It is even in the formula, even if you don't, let me tell you, even if you don't even quote it, you just say tick because you know it is even there in the formula. So what you're having here, it is resistance at the triple point RT. You see that? So they are saying what will be the resistance at 100. But remember, we are dealing with kelvins. That thing is very important. So they are looking for the resistance, but this time round at 100. But remember, we are dealing with kelvins. So you're supposed to convert this one to 73 kelvins. That is the first thing. Now the problem people make is just using it like that without showing the steps of how they converted the stuff. That is really bad. So let me show you the summary just here below. How would I attempt this as a student? I would come and be like, okay, that was resistance at triple point RT, okay. So they are giving me, so you know that the temperature that always comes in else is the theta, but here they didn't say theta, they just said at 100. So it is you to come out and say that that is theta. Okay, you people, you listen to me. In most of the cases, for you to let something, you can let if it is the unknown. But someone will be like, why aren't you saying let? I'm not saying let because the value is there as 100. So I'm just labeling. So this time around, it is labeling. But letting is usually for something they are looking for. So you let it to be something. But here, we are just labeling. And they are telling us that the R at theta is what they are looking for. So you put the question mark. But then you know we are dealing with the Kelvin scale. Someone may be like, how did you know the Kelvin scale? I told you that if the question does not mention that Kelvin scale, it will at least say what? Triple point of water. So it is up to you to be like, oh, triple point of water. This is where really the Kelvin scale comes in. So you're supposed to have all your values in Kelvin. Are we together? So I will really beg you to even wait to have this. Yes. As a student who realize that immediately after saying theta equals, you come immediately and add 273. No wasting time. Then you be like, this is 373 and this is kelvins. Then you put the semicolon and then say, the resistance at theta is what they are looking for. Now, since you are having theta, you're now dealing with the things you know. Now let me teach you something else. It is called playing with the formula. This time round, they don't need theta. They don't need theta. They don't. The theta is actually present. So when you come and say that theta is, we know that r theta is supposed to be on top, then down you're supposed to have RT, then this side we are supposed to have this 1, 6. You people, they are not looking for theta. So this formula will give you a time. So as a physics student, I advise you, every time they're asking for something and in the formula you have it's not the subject. Are we together? Like in this formula, theta is the subject. But every time they ask you for something, but it is not the subject, if you can first make it the subject, the better. So in this case, since they are looking for r theta, I advise if you can make it the subject, it is okay. But if you don't want to make it the subject and you want to substitute, then make your math, it is also okay. But me, I would advise someone who would make r theta the subject and say that if I make r theta the subject, I will have theta, okay, and that theta shall be multiplied by RT and then all over 273.16. Then use this formula. That is accepted in physics and it is liked so much because it makes the substitution easy, and from the substitution you just go straight away to the answer. The problem with using the other one, let me now try to educate you all. If at all someone comes out and say, for me, let me use this one, you come and say theta is 373, r theta is what we are looking for, okay? And then RT, we had it in the question, and it was, let's check, RT in our summary, it is 5.16. So you come and say 5.16, and you say times 273. It is very few people who can get r theta from that thing. I don't know whether you're trying to get me. But a student who is good at math can be like,
Could you try again?
keep quiet. And a student who knows math can be like, I'm going to get this, or I multiply it by this, then I divide it by this. I don't know whether you people see that math. Yes, I believe you're tired, but at least you can see that. Remember me, I hate cross multiplying, so I want us to talk of telepathical math. I talk what you see and you must accept. So that is okay if you want to move that way. But me, I support so much a student, if you're good at making something the subject, go for it. So that after such a step, you come and say now r theta. It is theta times RT. You be like, what is theta? It is 373 according to the formula. Sorry, the summary. Times RT. What is RT? You say that RT is my 5.16 over the value 2716. Now, do you see that here it is very easy for you to really just put in and get the answer? And please befriend these things so much. As you progress, when you reach those lessons of circular motion and simple harmonic, the waves, actually the waves you're covering, you can check them. All these principles are there. Where you're asked something and in the formula you have it's not the subject. You can use the formula like that, but it may call for unnecessary workings. But if you can really make it the subject, the better, because it will make your substitution clean to one extent that it leads you to the answer direct. I don't know whether people get that weighing scale. You just tell me in the chat that we get, so that you represent the people who will listen to this in the future. When you say we get, that means it is compulsory to them to get. Because for you, you're having a live class, for them, they're having a recorded class. That means they have that ability to even replay, to re-get the concept. So do you really weigh those two things well and you get the point? Okay, that is good. Now, we are ending the class. Yes, those who are tired, yes, just give me 5 minutes. Don't you see the assignment is near? Now, these are the numbers that make you an engineer. If you're there and you want to be an engineer, it is your time to shine. Are you seeing those things? They even look hard. Are you seeing them? Very hard. But trust me, if you by mistake understand what I'm going to explain, physics is going to just become your friend. Yeah, this is the last thing, but it is the cheapest. It is cheaper than what we have been covering, but technical. And after there, it will be assignment. Assignment, you will just take a picture. Let me see if you have a similar number. You people, there are certain questions where you will not have a similar number with those that I've done. That's why when I'm giving you assignment, I always advise you to at least first do my numbers first. When you do my numbers first and then you handle the assignment later, it's really nice. Yes, because you will first, you will be hearing me as you're doing what I did. Then when you reach the assignment, you feel like a goat. You feel full and great of content. So you just be passing things. So these ones are very cheap. Yeah, these ones are very cheap. When you see those formulas, they usually look like quadratic equations. When you see them, you just know that the things have really worked out. And I want to give you this last number as assignment because for it has alpha. I want to see if people can, I don't know, maybe. Remember, you're the same people. So whoever is going to listen to this, and when you try out that number, you will not get the answer. I'm going to put for you the answer. If you don't get that answer in the future, you're supposed to remind me so that in one of the classes we revise, you tell me to bring back that number and we go through it. But I'm going to give it to you. I see people can reason well and handle that alpha well. Yeah. But let me tell you, I just need to do for you one number. When I do for you one number, the rest are going to be doable because they are always the same. They are always looking like that quadratic equations. Even when you check, I think the book is Roger Muncaster. Let me see. I think it is this one. Roger Muncaster. It is there somewhere. No, it is longer. I read these books too much. You come and read these points. They are very nice. You see, the same way we are defining work. Pure water vapor. Yeah. Yeah. I love this book. So let me show you what I mean. Those who may want to really go an extra mile and look at that expression I'm giving them. I want to first show it to you in the notes before you can find it in the calculations. Let me see here. Are you seeing what I was telling you? That there are those books of physics you're going to come across, and for them, they are using 2.715A, not 27G, not just, you understand? Do you know those values of acceleration due to gravity? It is 9.81 in physics. That's what we use. But you can find a question telling you to assume it is 10. There are questions that will tell you to assume it is just 9.8, and you're supposed to use those values. So when you find those books, don't really feel bad. Do you see? They are attaching those temperatures 373.15. Do you remember when I gave you the absolute zero? And I told you that. Yeah. When I gave you that when we are talking about the absolute zero here. Those who try to notice, and I also said it, but I didn't write it. That's why I told you that you're supposed to always be sober. It's here. Do you see? We say that absolute zero is the 0 kelvins, and we said in brackets it is this. So if at all you have a very keen eyesight, you could notice. And I told you that that value is like that. When you find a 2.73, it is okay. The 0.15, you can use it, it is also okay. When you look at the final answer, it will always come out as the same. Yeah, so it depends. For me, I'm obsessed with both values. Yeah, because for the time I've taught the subject, I used to use 0.15. Then the next year I used 7.3. The next year I used 0.15. Now last year I was adding 0.15. But it is okay. 7.3 is okay. So you can consult more from your teacher and tell your teacher, what have you been teaching? Because it is very okay and very good to be in good terms with your teachers. Ask your teacher, what have you been giving kids? What should I use? If they tell you what to use, please, you go on with that. It is very good. Okay. Now, I was trying to show you here in Mooncaster that when you check these values, let me show you something here. If I forget, do you see the formulas? Very cheap. Are you seeing this thing? They are always like that. The nature is always quadratic. Yeah. So if at all you're applying any given principle, it will always be like that. It will always be like that. It will never change. Do you see? Quadratic. I think we are also going to get some good numbers from here. Yeah, I'm going to give you some good examples, sorry, some good assignments from here so that you can really try them out. Yeah, you have seen some nice work. I'm also supposed to give you this book so that you have it. Where you get confused, you visit a textbook once in a while so that you don't leave the level without looking at what really those textbooks have. You really feel bad as a student. Okay, now you come and read the question. How are questions said and how are they attempted? So I want to first give you a chance. You as you, I'm giving you strictly 30 seconds. You read that question on your own before I read it, because I may be a dictator and I want you to first interpret it in your own way. You first read it, you look at the words there, then after we read it together, then we see. I see what I want to tell you, whether it will really work out for you. Okay? You first read it on your own. You can even read the second. You try to check the similarity. I've been trying to clear my voice. Then we read it and it is cheap. I just want you to read it. When we read it, we identify what's missing, what we need, things like that. Okay, I think that is enough. Okay. Now, you people, triple point, you can also find it as TRI. So when you see something like tiara, that is triple point. But anything that you use, let no one put you on pressure, please and please. Okay. Now, what is this question saying? They are saying that the resistance R theta, okay, of a particular resistance thermometer at Celsius temperature theta, are you listening, as measured by a constant volume gas thermometer is that calculate the temperature as measured on a scale of the resistance thermometer, which corresponds to a temperature of 60 at the gas thermometer. I just wanted you to read it and get confused first, so that when I read it, you're also still confused, so that you go back and read this heading. But they are telling you that you're determining temperature on a scale of one thermometer as read by another. Are you seeing? that it is now the equation trying to relate the reading of the two. But let me tell you, this does not stop you from understanding how the unknown temperature is obtained. I want you to listen. I want you to listen. This number is very cheap, but you can make it hard if you want. But it is actually cheap. So I don't even want you to overthink. The moment you see two thermometers being involved, that does not mean that you go away from the norm of obtaining the temperature. The moment you see Celsius temperature or Celsius scale, you just know ice point and steam point are very important and they are going to be used. Yes, you just know they are very important, they are going to be used. That is non-negotiable. So you first write the formula. You see, in some of the cases, before you even have a clean solution, first write the formula and see what do they need, what do I have, what do I need, what don't I have, things like that. So I'm going to write the formula here. Remember, they are looking for the unknown temperature. That is it. Because they are saying calculate the temperature as measured on a scale of a resistance thermometer, which corresponds to a temperature of 60 at a gas thermometer. Are you seeing that? You all know, if I told you you're to look for, if I told you to look for the unknown temperature, you come and be like, this one is R theta, this one is R100, and all of them are supposed to be R0. Even this one is supposed to be R0 times 100. You see that? Now you people tell me, where am I going to put the 60? Where am I going to get, do I even have the R theta? Like, where am I going to get the R theta? Things like that. I don't know whether really people are getting me. You look at that formula. When you see a question having two thermometers and there is that funny equation, for you first have the equation. Because they are looking for the temperature. So you like it or not, you need this theta. It's what they need. But remember, they are giving a certain equation. Let me put it for you here on top so that you see it very well. The equation is that for you to get R at any temperature theta, you simply get 50, okay? Then you add 0.17 multiplied by that theta. Then you finally add on the 3 times 10 power negative 4 multiplied by the theta squared. Do you get? They're just telling you at any temperature they don't care. So when you read that question, you'll be like, oh, you'll be like, that means I can even get R0 because R naught means it is R at 0. That means if I come and put here R naught over R0, I come, I put here 0, I come here, I put 0, I can get R naught. You'll be like, oh. Then you'll be like, I can also get R100. In case I come here and say R100, I come here, I put 100, I also come here and put 100. You'll be like, oh, I can also get this. R naught, I can also get this. Then you'll be like, that means to get the theta they are looking for, I'm only missing R theta. So people, I'm asking you, where is the R theta? I don't know whether you're getting my interpretation. First write the formula because the norm doesn't change. When you write the formula, look at the Chi equation. The Chi equation is like, they are telling you the resistance R theta at any Celsius temperature theta, any, whether it is 0, whether it is 100, whether it is what, that's the formula you use. So if you need the R at ice point, that is R at 0, that means you can come and substitute 0 and get R naught. You can substitute 100 and get R at 100. Are we together? Where am I going to get R theta? Where is that theta? I don't know. Can someone unmute and say? Yeah, I'm going to send the PDF. Yes, I'm going to send it I'm going to send a link that you can use to download it. I'm going to send it on the channel. But I sent it long time just because people didn't give things time before things became tough. Now, people, you look at that. Where are we going to get the theta? Sorry, r theta. R theta is going to be part. R theta is going to be, is it really going to be part of the answer? Should we leave it in the unknown? Okay, r theta is simply r at any theta. And then in this case, we are having this angle 60 that has not done anything. I know that people are getting. You people, we are measuring resistance of a particular resistance thermometer, but we are measuring it using a constant volume gas thermometer. That means they are sharing a temperature. You understand? So this equation you're seeing, they are saying that equation is by a constant volume gas thermometer. That means they are asking you for the temperature that will give a reading that will correspond to a 60 on a gas thermometer. You understand? That means they're asking for theta that is going to correspond to this. So that means when you get this 60 and you substitute it here, you're getting the r theta we are actually supposed to substitute here. I don't know whether people try to get that. It is really very hard to understand, but when you get it, that is it. Do you people try to get me? Is that after doing all the interpretation, you realize there is that one temperature that has remained. But remember, it is temperature at a gas thermometer. And even the temperature or the equation, actually, the equation you have is for the gas thermometer. So that means it is very okay to substitute that value there. You understand? But remember, the resistance you will be obtaining, it will be resistance for the other partial resistance thermometer. I don't know how people are getting. So the temperatures we are using, these ones of 0, 160, they are the gas thermometer. But in the end, the resistance you're getting is for the particular resistance thermometer. So they are connected in that way that the temperatures can be shared. Okay, you can juggle the values like that. But me, I always just advise students, for you interpret it, you always find it in the end that, oh, this 60 is remaining, and when I put it there, I can get r at 60. And I think that r at 60 is my r at theta because it is the only thing that is missing. And it will be the same throughout. It will be the same throughout. You like it or not. So do you people try to get that? Now, I want you to get me R0 and R100 for me to confirm that really you people are following. Get your book, get your pen. After all, these are the last numbers. The next thing is assignment. Yes, the next thing is assignment. Yeah, the next thing is assignment. So we have our time. So I want you to be sober in the last minute. So I want you to get me R0 and R100 if at all you got what I've been talking about. Yeah, get me R0, R100. Those two, first get me those two only. Yes, first get me those two only. Hey. And please don't go off, don't sleep. Get me R0, R100. Then we begin the interpretation again from there. Yeah, so that now you take home real content. Yeah, then you go. But please make sure that as you're practicing, begin with my numbers first. And after my numbers, then you understand. You can deal with other things later on. Yeah. Do people have same values in the chart? How can people have different values? I'm seeing 50, 70. I don't know why for some reason people have different values. I don't know why it's like that. You see, that's what I hate. I don't know. Why would you be having different values? But I think, okay, let me check. Yeah, yeah, 50, 50. Yeah, I think you people have tried. Yeah, 50, 50, 50, and 70. Yeah, that is good. Okay, now I want to educate you a bit. First and foremost, people have asked me some good questions in the private chat, and I've liked them. Let me share the screen again. So let me briefly talk about them so that people can get the concept. Why are these ones really together? Where is our screen? Okay, so we are back. So I believe there are people who even already have the answer of theta. So the people are focused. And that is so good of you. So I want to show you something here, very small and so important. When you read this statement, what do you really understand? I'm going to just make these statements and you're supposed to later on write them on your own and make sense out of them. You read here. They are saying the resistance R theta of a particular resistance thermometer at Celsius temperature theta as measured by a constant volume gas thermometer is that. Calculate the temperature as measured on a scale of that of the resistance thermometer, which corresponds to a temperature of 60 at the gas thermometer. If when you read those two things, of those two thermometers, which one is inaccurate? Which thermometer don't they trust? Now this one is not physics, it is English. Yes, let me remove all this because we have already interpreted. You tell me, people, according to English. Yes, you read those statements well. Which thermometer don't they trust? Which one don't they trust? The one they are like, this one is inaccurate. You read it well. Because they are saying the resistance R theta of a particular resistance thermometer at Celsius temperature theta as measured by a constant volume gas thermometer is that. Calculate the temperature as measured on a scale of the resistance which corresponds to that temperature. Which thermometer don't they trust here? Which one do they claim to be inaccurate and they don't completely trust it? If we just read that English and tell me what you think. If you fear people seeing your message, you can send me a private message. Which one don't they trust? Even before going into deep details of which one do they trust, in the first case, you'd ask yourself in the first place, why would really a gas thermometer come and get involved with resistance? You all know the constant volume is to do with pressure, isn't it? But again, it is engaging itself with resistance. That means this resistance thermometer that is supposed to work on its resistance, they don't trust it so much. It is kind of inaccurate. But remember, in the end, you people, I can have a basin of ice. I put there a resistance thermometer. Are you listening? I put there a constant volume gas thermometer, a constant pressure gas thermometer. I bring a pyrometer. Okay, I put there different kinds of, but in the same basin of ice. Do you understand? So don't be confused about that point, but just understand these are all thermometers. In the end, they are supposed to be helping us with measuring what? temperature. Okay, so after appreciating that, also believe me or agree that this first thermometer of ours, it is rendered inaccurate. Yeah. Why inaccurate? They don't trust it. That they are supposed to go through the gas thermometer to really confirm whether things are really happening. You understand that it is the gas thermometer that is going to give us right values. So whichever temperature we get or whichever temperature we are interested in, we are not supposed to just read everything directly from the resistance thermometer. That is very bad. That's why they provide an equation that can really assist us with the right values of resistance. Are you people getting me? That when you just get this, because someone may be like, why didn't they get the resistance thermometer and dip it in a basin of ice to get the R naught, because it is R at ice point? Simply because they don't trust it. It's going to give you a wrong value. But if at all we are interested in R at 0, they are giving us an equation provided by the gas thermometer because it's the one trusted. So that equation can help us to get the right resistance that the other thermometer is supposed to give, even when it doesn't give it. Do you understand? So understand that the moment two thermometers come in, there are a lot of trust and mistrust. The other one that really comes in is the one that is trusted. So we are supposed to use it so much. You understand? So if we need R0, we are supposed to come here and feed it in because it is the trusted formula. The first one, it is not trusted at all. If at all we need a R100 or at steam point, someone will be like, why are you getting the ice and steam point? Because we are talking of Celsius watt scale. It needs those two fixed points. So you come and substitute 100. I know some of you have substituted poorly and I'm going to substitute for you. Okay. Now, when they ask you for the temperature, I want you to listen here very carefully. Since, okay, they are trying to mean that for them, they know the value they want. But when they get a resistance thermometer and a constant volume gas thermometer and dip both of them in the ice, they know the value they want. My dear, the one of the resistance thermometer does not give you a right value. Remember, it's supposed to give you 0, but when they put it in ice, it is inaccurate. Someone may be like, how did they know it is inaccurate? They dipped it in ice and it didn't give 0. That means it is inaccurate. But the gas thermometer did it. So we can have an equation that can relate the two and give us perfect readings. Are we together? So when they ask for temperature and again give you temperature, they are like, please help us get the temperature where the resistance thermometer will give us the same resistance as that the gas thermometer will give us at 60 in this equation. Do you understand? That for them, they know one thing. At 60 degrees, since this one is inaccurate, they cannot be having, okay, 60 degrees cannot be given by both. If at all we get water and it is at 60, and we dip both of them, it is the gas thermometer that will give us a 60. The other one will be giving you wrong values. That's why they are like, they really want that temperature where we shall have that true resistance. So it's like this gas equation is there to substitute for this theta. So when you substitute for this theta, you will be getting a value of resistance. So that value of resistance is the true one. So in the end, you can now use it to find the temperature that will give you that true value. I don't know whether you just need to get the story. You don't need notes about this. But understand one is trusted, the other is not trusted. So what is trusted, the equation is always provided. Remember, I gave you the old technique first of doing things manually. Now this is the physics. Okay? So the one that is trusted, there is that equation. So when they ask for temperature and also give you temperature, someone may be confused and be like, you're asking temperature which is at 60, what is that? So that simply means you can never have the same readings at the same temperature. You can never. So that's what brings in the concern. So for your rays, just do everything as we've done there. Get the ice point, get the steam point, get at that temperature. You've obtained R theta. Now go and use the other formula, get the temperature required. That's why it is handled last. It is really too technical. But then more people have tried to get something. Okay? You look at this. You look at this one. Let us see what they are saying. They are saying that the value of the property X, here they have not specified which property, but they have said of certain, the value of certain property this, so they are saying xt. So this is as simple as the value of that property at a temperature T. That's what they have said. But they are telling you that T is in degrees Celsius. That is very important, that it sends you to obtaining X naught, where T will be 0 degrees, and then also X 100, where T will be 100. So you can also obtain these. So what are they saying? They are saying what will be the Celsius temperature at 50 degrees on this thermometer scale? Do you see the confusion? That they're asking you for temperature. Again, they are giving you temperature on 50. So it's like they are playing on your mind. So as someone who really knows what they are doing, you will come and be like, oh, you want temperature at 50 degrees. Before you come and write the formula, you be like, may I know that temperature you need is unknown, so it is theta. So I'm going to come and say theta. You all know you're supposed to get, now this one is X. They have called it X. They have not specified which property. So you come and say this minus X0, X 100 minus X0, then times 1000. Then you be like X0, this one I can get. I just come and put here 0. I just come here and put what? 0. You understand? But remember, there is X not here. But I'm going to teach you. This one is very cheap. We are going to do it together. Don't worry. Then you be like X0 I can get. Even X 100, you be like I can also get. Isn't it? You just come, put 100 where there is T, put 100 where there is T. We are going to do all this work. Then you be like, they need the theta because they're asking for temperature. Now, since they need the theta, you are lacking X theta for you to have the answer. So you ask yourself, where am I supposed to get X theta? But you be like, there is this idle theta in the question. What is it doing here? So you be like, that means I'm supposed to get this theta, put it there, get the X. After getting the X, now get. So have it in mind, it's always about inaccuracies. That you will have different values of temperature, but giving you the same value of the thermometric property. So somewhere, somehow, the thermometric property is not changing linearly or continuously with that kind of thermometer. Do you understand? So it really gives you part time that they are asking. Do you see? They are asking for temperature, but again, they are giving you 40. So the 40 is supposed to fill this place. Then you get this. As simple as that. So I want people in the chat to tell me we've got it. I don't want you to tell me somehow because I've over-explained, even the head is aching. You just tell me we've gotten it. Yes. I think we have tried our level best to handle that last part. Yes. Do you remember when they talked of interrelations in the syllabus book? These are the interrelations they meant. Yes. And that's how they apply. You're supposed to handle things manually, see what is missing, see what you have, see how manual work can help. Okay? But at least we have really tried our level best, and I think people have gotten it. So how do you really have your solution? When you look at this first one, these two numbers are different. This number is different. Let me reshare the book. But that number 1 is different from number 2. Yeah? Because when you look at 1, it doesn't have, okay, it's only having arrow on the left. But when you look at number 2, okay, let me share it again here. Sorry for that. So you people, that is it, That is it. So I was telling you that when you look at this arrow is only here, like this side you don't have any arrow, you only have theta. But when you look at this one, you also have some x this side, and also the theta, which is this time round t. Okay, so we are going to do both numbers, but they are cheap if you've gotten the concept. So their solution is always very easy. Don't even waste time. First write the equation. So we are going to come and handle that. Let me even say mixed problems, the interrelations. But you're supposed to practice. It is okay to do one number over 10 times. Very okay. So we are going to that r theta. What do we have? Okay, r theta. Where is our book? It's here. So it is 50, 0.7, then 3 exponent negative 4. Hope I recall. Okay, it is 50, 0.17. This is theta. Okay, then this is 3. Okay, now when I ask for r as 0, this is the problem most of you are doing. Most of you even just said it is equal to 50. Because according to you realize when you put here 0, it will turn 0. Even here 0, but you're supposed to show that work. Yeah, you're supposed to show that work. That's where most of you go wrong. You don't respect what they call substitution. You're supposed to come and say plus 0, then also this one, exponent negative 4, but also you show the 0 at squared. Okay, then you come and finally say that that one is what? 50. But this is resistance. So don't forget the units at least. Then also here you can try to be clean and tell these people that at 0 degrees Celsius you're getting R naught. Okay, then you also come and get at 100. The moment someone tries to ask you why are you really getting at those temperatures, you simply tell them I'm dealing with Celsius scale, and with Celsius scale at least there are 2 points that are fixed, so I need them, and that is ice point and steam point. Ice point at 0, steam point at 100. Okay, so you come and say 50. This is 0.17. So here it is 100. So I'm just using the substitution above, and where there is 0, I'm simply putting 100. So this is negative 4, okay? Then this is 100, and this is squared. So you people said you got 70, isn't it? And it is resistance, so never forget the ohms. So you get, oh, these are max. Substitution and the output. Then I told you that 60 they have provided, it is very important. And trust me, the formula is going to change. That's where most of you go wrong. Because most of you have been seeing theta, theta, theta. You're going to make a mistake and have r theta. Remember, r theta is supposed to be for the very theta you're looking for. Yet we don't know it. So you're supposed to come and say r60. So you tell me, what do you have for r60? 0.17. Then here I'm going to have the 60 plus then 3 times this is this. Then I also have this side, the 60, okay, squared. We also need the r60. Let me see in the chart. If people, what is the 60? You're not telling, is it the 61.28? But it is impossible. That cannot be the value. Why would we have points? What is r60? You people who got the answer already, what is r60? Is it the one? The one I'm getting, the 61 point, I'm seeing it in the chart. Okay, I think let me try to get it myself because I have trust issues with people at this time because I know it's only me who is halfway sober. But me, I don't normally give up, not until I hit my target. So it is 3 and it is exponent -4. Yeah, 61.28. That's what I'm getting. Yeah, thank you so much, Kate. Yeah, 61.28. Yeah, I've also gotten that. Yeah, so substitution and the answer. So what I like about this number, it's having a lot of marks. Very good work. Now, when it comes to the formula, this is where people mess up. And I don't want you to mess up. Yeah, I don't. And please don't risk. Don't risk. Because now people may end up coming to say that we are looking for theta, yes. Then they come and say that this one is going to be our theta minus, okay, we all know this is r naught. Then we all know that this is r 100. Then this is r naught as usual. Then this is times what? Times 100. But remember now the problem is going to come from this is theta and this is theta. So the moment you do anything weird, the moment you put there 60, it's like it's going to be bad. So it's better that even in this first step you put there 60 so that you show the examiner in the very first expression that you don't even know whether those two are related. I don't know whether you people get me. So to be on the safe side, if you know that you're putting R60 there, put R60 in the formula. Don't put R theta. Don't. Don't. Don't stress yourself. Put R60, no problem. It is a formula that they will mark. But if at all for you, you're really not sure, you're really so scared, this is the technique I usually give people on that number only. I tell them that before you do anything, even before you write that, first write the formula here. You tell them that theta, I know it is r theta minus, you tell them r naught, then down you put r 100 minus r naught times what? 100, like that. So after having it there, you now come and do all this crap. After all this, you now come and write the formula. The formula that has 60. So the problem that most of you do, as I told you, that you just come and put your equal signs only, which is wrong. You're supposed to rewrite this theta also. So you come and say that this is 61 point what? Is it 61.28? Oh, I've forgotten, yeah. But never forget the units, please. Minus, this was 50. Then at 100, this one was 70. And this one was 50. Then times 100. Okay, this is now substitution. Then you get the temperature. 2 dPs. Okay? Someone may be like, but the one in the question was 60 and it didn't have dPs. Why do you want your final answer to have dPs? My dear, I told you never avoid dPs unless the calculator is the one that is avoiding them. But as a student, you're not supposed to. You are not supposed to. So I'm getting 56.4. Is it what you guys have? Okay, thank you so much. So you know the answer is supposed to have what? Units. And here standard form is not enough and it is 1 dp that the calculator has provided. So I cannot force decimal places. So for me, I will tick the value, I will tick the unit because I really need you to recall all this. So you look at that calculation and that's how things flow. If you have trust issues, first have it. First have the formula, come and do all this, then write the formula well, remove the theta, put there the thing you substituted, then have the SK substitution, then have the answer with the unit. Something like that. Very neat. Okay? That was problem 1. Now problem 2, I told you it is kind of special in a way that it's having x even on the right hand side, and people may say, you've not what. Let me do it, and then you do 3, and I also give you the hint for 3. Then I give you your research, we leave this place. Yeah, the lesson is going to be about 3 hours. Yeah, from 10, actually it's going to be about 4 hours. That's too much. Yeah, but provided I hit the target, I don't care about the rest. Okay, now let's see this question. Okay, I think that is it. Let's look at this. It's xt showing us that the property value at a temperature 10 degrees Celsius. Okay, this one is 0.5 and 2 exponent -4. So I'm going to come. So hope we are still together. Same page, and all of you are listening, voice clear, screen clear, and you are understanding. Hope you're seeing light at the end of the tunnel. So let me secure our document, and then we handle the second case. I think the document doesn't want to be secured. Okay. I told you that for you first now write the formula, but remember here they have used the xt, not like before where we have been using x theta. So you really need to be careful with all that. So I'm going to come here and say that the temperature they might be looking for this time around, it's not theta, it is T. But someone may be like, are you really sure? My dear, you read the question. The previous question had theta, and that's why we also had theta. My dear, this time around it is T. So you're supposed to respect all that. Yeah, the moment you cram, you're gone. So T, instead of R theta, we shall have R T minus R naught can never change because it's like saying the ice point changes. Then we shall have R 100. Then we shall also have our R naught, not forgetting the times 100. Someone may be like, why all that? Why that formula? Because we are dealing with the Celsius scale. How did I see that? They mentioned it here that the temperature, small t, is in degrees Celsius. So I need those. So you realize the temperature in place is 50, and they're also asking for temperature. So you also play on their mind, just like the way they are doing on ours. Okay? So after having your formula, now for you start, be like, okay, this is what they gave me. They gave me xt. Then they came here, they put x naught. Okay? Then they came here and added 0.5. And they add the t. Then they got 2. Still this time around exponent -4. This time around it was t squared. So if you come and check, think they are the same. Do you see that? Now I know I need to get 0, 100, and 50. But now this time around I have x naught somewhere. That's why I'm doing this for you. So I will come. Remember, x naught will not change. X naught will not change. So if I come and say at 0 degrees Celsius, what are you getting? Of course, you're getting x what? X naught. Then you substitute. People, get your calculators ready. I don't want to reach a point and we are just struggling. Okay, so you shall have x naught here plus, I told you we are supposed to substitute here. You shall put a 0, even when you know the 0 cancels everything. Yeah, then according to math, for you just do the math. What you are getting here is that x naught will still stay as x naught. Yeah, don't overthink and say, but if I put them on one side, they cancel. First leave it like that, because my dear, you'll need it. Okay, so first have it as x naught. So x naught is x naught. It's not being helped. You'd be like, things are hard. Because most of you, if you had reached that point, you would be like, the question had a mistake, yet it didn't have, okay? So we go to 100. So we'd be like, what over 100? 100 x 100. Okay. X naught is not going to change. After all, X naught is still X naught. Then the others I add. Yeah, you're going to see the beauty. So get ready to tell me the value we are getting this side. Then this will be 2 exponent negative 4. Then the 100 will also be coming with a squared. So tell me, what are we getting? X 100. What are we getting? X naught plus what? That's what I want to hear. To see if really people are sober. I may be and I'm talking to myself and no one is really here for me. Something that is really very bad. Let me see the chat. 52. Okay, now prepare answers for 50. Eh? So this one is 52. Okay. Yeah, I think let me use this space for 50. People, why 50? 50 is the one we have in the question. Yeah? So you come and get x 50. So you come and say it will also be x naught. Hey. So you appreciate in the end, yeah, that as this x naught keeps around, in the end we shall subtract and it will cancel. It will cancel. It will cancel. So don't worry. It is just algebra. This number, even if I had not tried it with you, trust me, it would really come out. If at all you had gone with it as assignment, it would really come out still. So this is 50 and this is squared. So what are you getting? X 50. What do we have? We're having x naught. Which value are we having? You people, you're not fast. You tell me the value. 25.5. Okay, thank you so much. Okay, so those are the values. Now after, for you know they are looking for the temperature unknown. You people, the temperature is T. Have that in mind. Don't risk and have theta. Hey, that means you are copying. You're just cramming work. Eh? So when you reach here, this X shouldn't be T because now this T and this T will create suspicion. So the best thing is to have what you're really going to substitute. So me and you know that here we are going to put there x50, okay? Then here we are going to have x naught, that one never changes. Then down we shall have x 100. Then this one we shall have x naught. Then times 100 and we shall have our answer as degrees Celsius. Are we together? So you're going to appreciate that the x naught staying in our things is actually a blessing. Yes. So x 50, you all know it has been x naught, okay? Plus, I think it has been 25.5. Okay, you can even decide to have it in brackets, then minus x naught. So you don't know whether people are seeing x naught cancelling. Hey, even this one over 100, yes, you still have x naught plus the value, I think it was 52. Then also minus x naught. Then times the 100. So do you see? That x naught staying there is actually a blessing. No physics at all, just math. So from here you can try to simplify, but even if you don't, but then this is what they call evidence of working. If you really need to show it, then you get your answer. Temperature in degrees Celsius. So I also want to see that value in the chart. People, hurry, 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 hurry. I told you to get your calculators ready. So that when I ask for the value, have active people and they just tell me the value there and then. 49.04. Let me just trust that person. And of course, degrees Celsius. So if I come as Paul tutor and I'm supposed to mark this number, I will appreciate the fact that this student knows what they are doing. Rewriting the expression is no mark. As they are getting at 0 substitution, they need a score. then their conclusion. Then also at 100, they need a score and their conclusion. Even at 50, their substitution and also their conclusion. Then we're writing the formula that really is going to avoid errors and red flags. I give them a mark. They substitute very well. A SCA model now. Then I look at their computation, their evidence of working. I give them a mark. Then I come here. I appreciate their value. I appreciate their unit. I mean, that's how I mark my work. Provided you just write things the way I say them. Most of you have a tendency of leaving out this, the T equals. You just write things anyhow. That is very bad. Just from today onwards, handle calculations as a student of Science Scholars Academy. Have a summary if needed. Just have nice flow. The way the work is flowing here is the same way I expect things to be flowing, okay? Now, number 3 is yours, and this is assignment. Let me hope people have been taking screenshots for the different assignments I've been leaving, because at least I've been giving you a chance to take the screenshot. So this number 3, you like it or not, this one is assignment. Why? I'm liking it because it's also having R not there. It's just math. They're asking you for temperature, but again giving you temperature. But you realize that this one still has alpha. So we have agreed, me and you, that this one will always cancel. And then also this alpha is going to cancel. Yeah, it's going to cancel. Have that in mind. And when you calculate everything perfectly, I expect you to get, this time round, theta is what they are using, and I expect you to get your answer as 16.06 degrees Celsius, because they are telling us degrees Celsius. That's what I expect. So let me hope you people have been calculating things. Okay? Now, there are certain numbers we left as assignment, but people were not. Okay, people told me, as if people told me this number was doable. I don't know. I think we calculated it and stopped somewhere. But let me also give you its answer so that you be aware. So here the answer we expect. 0.5, they're asking for resistance. So you shall need those ohms. Okay. Then even this one, people said it was doable. So let me also give you the answers. Hope you're taking screenshots afresh. I'm tired of pleading. So yeah, they are asking for temperatures. So for the resistance thermometer, if you calculate well, you will get 39.55, and it is Celsius, so degrees Celsius, okay? Then for the gas thermometer, when you calculate very well, you will be getting something slightly that, and it will be 96. Okay, very important. Then what else? What else? Is there any other number that we didn't? No, let me see. I remember this number 2. You told me that to leave it. I think it was just looking obvious. Hope you people are taking screenshots again. So that number, if you calculate well, they are looking for temperature theta. So the theta will be 125. So when you get your answers, you should always advise people, especially for physics, because I believe in numbers. As I leave a number, you can also be doing as we are progressing. I leave a number, you do it as we are progressing, something like that. Yes, and thank you so much for being in class up to this long. It's almost 3 a.m. Yes, I don't take that for granted, even when the questions are handled at the end. And that was people's goal. But we don't care, provided we handle things very well. So you first take that assignment as well. Yeah. But there are things you really need to concentrate on. You can see these answers are in kelvins. So it is okay to have your answers in kelvins, degrees Celsius, whatsoever. So you first also have those numbers. But as you know, assignment, the very first thing is you doing my work, the one the like examples I've been doing, and you also under the assignment. So that number 3, this one, I've given you the hint that try and see how the R naught will be cancelling, and also the alpha, because the alpha is just there to create chaos, so it should leave by all means. Yeah, you just need to be doing the right math. Now this is the chapter that I told you that it is yours. Yeah, this lesson, I think it is 5 hours. I think it is 5 hours. Yeah, 5 hours, or maybe 4 hours something. So this is yours, and I'm just going to guide you on what you're supposed to do as research. Yeah, so here you're supposed to talk about the types of thermometers. They are here very good notes. So liquid in glass, this one we watched the video. Whatever is here is actually on the video. Okay, but we shall also look at them. But after you guys presenting, I told you we shall respect the competence-based curriculum at some point, where some of the work shall be handled by students in a way of presentation. So it will be student-centered for some chapters, but for the critical chapters, I'll be handling them. But don't worry, even after you presenting, we then cover them as a class. But then the problem is one that the other classes may be premium, which I may not really want so much. But have it in mind, the next classes, as far as it is concerned, they shall be premium. The calorimetry, the heat transfers, the heat quantities, gas laws, and then thermodynamics. They will be completely premium. So you please take note of that. Okay. Now you can see they are notes they are adding on this. Liquid in glass, what, reasons why mercury, why water, then you can see resistance, platinum resistance, you can see qualities, you can see the structure, how they are used, you can see advantages, disadvantages, things like that. Now for me, I'm going to give you something so simple. The research, you can see constant volume thermometer, and how it operates, the advantages, disadvantages. You can see the pyrometer, you can see the optical radiation, the total radiation. But have it in mind, for your curriculum, they say total radiation, you can leave it out. Hope you recall it, it's there. Total radiation pyrometer should not be considered. But as a PCB student who wants to do radiography, please, you learn it. It is something so short. And me, I will teach it, but I teach it after telling you that it's not supposed to be considered according to the curriculum. So you decide and be like, let me learn, okay? Then you can see its mode of operation, things like that. So these ones are miscellaneous checks for content mastery. You see, your curriculum does not allow these things of define and what. But as I told you, you need them for you to master the content very well. Are we together? So we are going to take screenshots for these cases. Those in the premium group, you're supposed to take these screenshots and post them in the premium group immediately for your friends to get highlights. Even others you post in other groups, others you can just keep them for your own good. So I put them in cases, they are just checks for content mastery. That if you believe that you've really covered this topic and you've understood, you come and check and be like, can I define a thermometric property? Can I give 4 examples? Can I state 2 qualities with reference? Can I handle this description? Can I state those advantages and disadvantages? Can I handle this calculation and get this answer? You understand? You're just checking yourself to ensure that the content is really mastered. Trust me, when you handle these cases, the miscellaneous cases for content mastery, by the time they tell you that the scenario of thermometry is somewhere, you just be like, bring it, and you just smash it in no minute. But if at all you just read and for you just want to straight away go into the scenario, that is very bad. Very, very bad. Okay. Then this is also case 2. Hope you're taking screenshots. You take that screenshot too. Half of case 2. Okay. Then this is continuation of case, do you ask yourself, can I define the triple point of water? Can I really describe how I can use a thermocouple to do something? Do I know those merits and demerits for the constant volume gas thermometer? What of the constant pressure gas thermometer? Things like that. Okay? So case theory. Ask yourself, near one, midway, the fixed points. Do I know the physics there? What are these things? Most of these things I've been saying. Now this one. Temperature on a Celsius scale. Defined on a platinum rate. That one, very cheap. But I want people to find time and read through them. I see if someone can inbox me one time or inbox one of the consultants and ask them, this is one of the cases doctors left for content check and mastery, but I don't understand this statement. What does it really mean? I took all screenshots from the class, but I don't get it. Even by chance have some solutions, you should thank me so much. Okay? Then this is case 4. You can also take a screenshot of that. Get time and go through. All the keywords were put in bold. Very good notes. Okay? Then I told you there are solutions for some. Hope you're taking screenshots. Supposed to just be very fast. You get a chance, you take. Then you're supposed to sit down and rewrite these things. People don't want to write notes. They just want me to send notes and they photocopy. But that doesn't work. You're supposed to write something. Every time you write something, it really sticks on your mind. So you please go through these checks. You can be like, I understood calculations. Let me first handle the calculation. That one you tick. You be like, let me see if I can get 400. Now you just come and tick these simple ones. Okay? Then you, things like that. You see? And then the topic shall be done. So you see, the next topic that we shall be handling is topic 10, and it is called heat quantities, or what we call calorimetry. And the very first statement we shall say shall be that, and that's where we shall begin from with calorimetry, and that will be strictly and strictly what? Premium. So don't expect to see this video free on YouTube. The rest of the things that are to come, calorimetry. After that, we shall have heat transfers. After heat transfers, we shall have gas laws, where we shall find the kinetic theory of gases and matter. Then we shall have the thermodynamics. So all these ones are going to be strictly and strictly premium. At least we've had an introduction for thermometry together. Don't take that for granted. Okay? That's where we shall see things of heat capacity. That's where we shall see things of latent heat, things like that. Now, what is that research work that I want you to go with and then present when I call presentations? Okay, I may say that in case people give me very good presentations for the research work I'm leaving now, I will say that I may say, okay, even calorimetry, we shall have it as a free class and we shall upload it on YouTube. Yes, I can say that. I can say that. For me, I can easily change my mind if at all students are serious and are really showing concern. So this is the research work that I'm leaving. Okay, this is the research work. Very serious. So the first ones are the liquid in glass thermometers. Yeah, the others they call the liquid in glass thermometers. Okay, then we have what they call the platinum resistance. Let me just say resistance thermometer so that you will give me the platinum resistance and the examples. Up here together. Then we have the constant volume gas thermometer. Yeah, the research is serious, but it will really make you a good person. every time you make your own research and make your own notes and you're understanding the things because you have an idea, trust me, you will enjoy A level. Because that work you make research on yourself on, and you understand the work and really write it. That is very good. Okay. Then lastly, we have the thermocouple, then the pyrometer. And you all know the thermometric properties for those. So even the research is going to include them. Even when I gave you the thermometric properties, I would want to see them again. So these are the things I expect for each of them. So what is the question or the task? I'm saying for each type of thermometer, okay, hope you're seeing the screen. For each type of thermometer, I want you to give me the examples. Like for example, the liquid in glass, you can tell me examples we have: water in glass, mercury in glass, ethanol in glass. If any, there are those maybe you may fail to get examples. After examples, you need to tell me the thermometric property for each. For each, then after I need the structure. I need the one from Pinterest. You just take a screenshot and keep it. Then I also want the one that is hand drawn. Yeah, Pinterest or anywhere on the internet. I don't know your interests. Okay. Then after the structure, I need the mode of operation. Then after that, I need the advantages of each. Of course, we said of each, then disadvantages. Then there is what I usually call extraordinary content. For now, the engineers that will be taking on very serious contracts. Yes, extraordinary content is not easy. Yeah, extraordinary content, someone may be like, what do you mean? You read the textbook, you'll find them. Things like inaccuracies. Yes, someone may be like, but that is under mode of operation. It is okay. Whatever you want. Inaccuracies, someone may want to compare thermocouples to pyrometers, things like that. So please also kindly take a screenshot for what your syllabus book has, so that people don't forget that the total radiation pyrometer is not really considered. You also look at the project work. It is very clear. This book is student friendly. When you read it, you get everything. Project work is very clear. In groups, you're supposed to model different types of thermometers from locally made available materials and use them to measure temperature. That's why I'm like, if at all I teach you these things, you may find that time handling that project work. So I just believe that if you first make some research, I come in, I hear people presenting, I award them marks, and then I also talk about everything, which I really enjoy. Okay. I've been giving you the work. So, and others. Yeah. So extraordinary content, you'll find it in textbooks that I'm going to provide. And the textbooks that I want us to be using, they are only and only 3. They are enough. Yes, they are enough. And I'm going to just abbreviate them. We have Neocon and Parker. To get extraordinary content, we have Roger Moncaster. These ones I've told you I'm going to share them in the channel. In case I forget, someone should remind me, those who are still here. Then also, we have Tom Duncan. Okay, then also I can give you some of the research sources. Sources, what they call references. Yes, of course, textbooks are references, but YouTube, that one I like it so much. Yes, you can use Google. It is the same company. I know that people are aware that YouTube and Google, it's the same company. I am aware YouTube is owned by Google. Then there is what they call Gemini AI, very good. Yeah, Gemini AI, very good. Does not expire. So you can use it. They are one of the sessions where I try to teach people on how they can really use AI, but it is not reliable. Not reliable. So I will warn you, not so reliable for now, but those people will study in 2020, 2029 to be so reliable. But at least you can get something, yeah? So if at all you can add it to textbooks, yeah, then that is so nice. Yes, you're still young, you're still in senior 5, you still have the time. So I think that is the work. I don't want to give you a lot of research work. So for now, really allow me sign out. Allow me sign out. As Paul Tutor. Yeah. One of the tutors at Science Scholars Academy Uganda. I don't know how long this has really been, but I just feel it has been too long. I don't know, are they 5 hours? Yeah. But let me tell you, it is worth it because most of you are aware that why I always want to have these topics as one session, because at school you may have thermometry in like 3 lessons. But remember those 3 lessons, each lesson is 80 minutes. Those are 240 minutes. Those are 4 hours. So if I can come here in 4 hours and I also do the same or even do better, that means it is really worth it. But people don't complete these classes. On top of dozing in class, even these classes, they find it hard to do what to complete. So, Science Scholars Academy, SSA, and this is, okay, you can see my contact there down. Let me hope people really took something on the, I don't know if people took a screenshot of the research work. That is very bad. But you're supposed to just write it. Eh? Those people who took some of the screenshots, you're going to send them to me. Yeah. Yeah. But I think even God wants me to rest. Because after all, the document has been taken by my guardian angel. But at least I've signed out successfully. And that is my number. You just leave a WhatsApp text. Yeah, these days WhatsApp calls are too many. Don't call. You leave a WhatsApp text. If I overdid respond, then maybe you can call, yeah. Otherwise, people, thank you for attending. Let me hear from Samsung. Let me see if people are really thanking me for the class in the chat. You have a tendency of not appreciating free classes.
Yeah, doctor.
Yeah, we were ready to make it to 6 a.m. Are you ready? Are you
Yeah,
sure you're ready for 6 a.m.? Because for me, I'm very sober. Because I
I'm
can
also
say, I said that I may say that we come back and introduce modern physics and we cover radioactivity.
I'm also sober, very sober.
Oh, you're asking what of calorimetry? That is the next thing, but it's supposed to come after thermometry. There are different topics according to the syllabus, so I cannot cover it now. If I'm to cover anything again this very night, we are supposed to now introduce something new. I need to see that work that I've given years research. I want to first see people presenting. We have a full year. This is just March. If I realize you're not serious, I stop there. I don't continue with that
Oh,
topic. There is light. There are so many topics in mechanics.
okay. So, doctor,
Yes.
on the other last assignment which you gave us,
Eh.
my internet had just blocked off, so I need some more elaboration on that alpha which you
Hey.
talked about.
I just said the alpha will also disappear. There is no physics. It is there and no one has really invited it there. So for you just do the math, the way the flow is supposed to be done. Trust me, you just see it going away. Did you see the X naught going out? You didn't really see that coming, that the X naught would really go away, but it went. So that's how the alpha will go. I think someone who has tried that number, you've seen the alpha really disappear. You tell people in the chat that it disappears.
Okay.
Yes, you're going to see someone in the chat telling you that it really disappears. And
Okay.
it really does.
Okay, but we appreciate you.
Okay, 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 okay.
Thank you for your time.
Okay, people, I think we shall meet again we shall meet again. I don't know physics. We shall meet again in maybe light, the free class. Then we are supposed to meet again in modern physics. That is, I don't know, maybe I will start with atomic particles, but most people were complaining about the quantum theory. The quantum theory, it is the easiest thing in physics, though the hardest thing in physics is quantum mechanics, although it's not covered at A level. But those are cheap things. Then maybe I will end with nuclear processes. Or maybe I will start with nuclear processes. I don't know anything because with modern physics, I can begin with anything that I want. But that one is very cheap. Now for modern physics, I'll get a lesson of 12 hours. That means it is supposed to begin at 6 p.m. in the evening and then it ends 6 a.m. in the morning. So that I'm covering modern physics up to when I complete it. Because that one I can. So I don't know if people can really settle for 12 hours. These are 5 hours, almost a half. So what really stops me from moving for more 6 hours? Something that is very easy. But I just be scared about the students. So they be understanding. You find different people attending different sessions and the session will just die like that. And people watching a recorded lesson of 12 hours is very hard for them. That's why I'm still avoiding that. But when I realize I'm dealing with very serious people, I'll do it. Yeah. So that is the plan for physics. Then I want to reach a time where I'm only having mechanics because the one I enjoy most and I want to have its special time. See these other things, the heat, the light, the waves, they have a part with a lot of Lugambo, which I like also, but I like so much calculations. But we shall be planning. I believe by the end of the year, we shall have seen light at the end of the tunnel. Those who are having premium access to the drive, you know very well that math we are done. We only need like 2 topics, permutations and combination and statistics, and the whole math is done. Chemistry, we just need, I think, only radioactivity, maybe bonding and structure, and the whole chemistry is done. So we are supposed to struggle with this physics for the whole year. Biology is only having a few topics. That one I can just come here and talk the whole night. That one is just in my veins. I'm a medical doctor. But then this physics, it has technical parts, it has calculations, it is very sensitive. So by the end of the year, if we can complete the syllabus, that means you have the whole of next year to just do revision. That means if you fail, it's really up to you. Yeah. So please, in whatever you're doing, plan well, plan well, plan well, plan well, plan well. Third term holiday, I just want us to be revising scenarios. When we know the content, each scenario we get, we just crash it. Each scenario we get, we just crash. So really pray for your parents and all your guardians to have the money to really support you to be part of premium classes because I really don't want anyone to miss. Yeah. I don't know if we have taken screenshots. Someone has just reminded me screenshots for the free class. Sorry, for the notes. I don't want you to take these ones of the thermometers. You will copy. Yet I don't want you to copy. But if someone was wise enough and they copied, that is good of them. So let's take these screenshots as we hear from, I think Precious has something to say. So take that screenshot, be fast. Precious, you speak. I've asked you to unmute. I don't know why you still don't want to unmute. Someone left on their video and they are sleeping. It is quite absurd. You take that one too, but are the screenshots really clear? Are they really clear? Because we may be taking them and they are not clear at all.
Yeah, so for me, I have a question. Like,
Yes, yes.
much,
Mm.
for me, I have a question. Like, how much are you going to pay for this holiday?
No, the whole combination is 100,000 for all the subjects, even ICT and GP.
So when are we supposed to pay?
When you can, people already paid actually. When you can, anytime, because from here I teach the whole year.
Then what if I pay in installments?
It is okay if you pay your first installment as 50,000.
Okay,
But
then that's
installments are always very tricky because we find it hard to follow up on students. And in most of the cases, they lose access in 1 week, yet they paid the balance and they didn't communicate, things like that. But you
but
can,
I'm going to try to pay in installments because paying 100K is a lot.
yeah, true, I understand. But
Yeah.
trust me, by the time you invest in 300,000 and you've covered all the work, because when
Mm.
the moment you pay for the holiday, we leave you with the drive for the next term, things like that. So 300,000 and you've covered work that has meant more than, okay, that will mean more to your results than what you will have obtained from school. Trust me, because these are classes you can visit anytime, things like that. You have them on your phone, you can rewind, you can pause, you can make notes. Okay, you do things at your own pace. So if you're serious and you look in, you can really benefit.
So there is something you have said. I'm like, you have said that if I pay for this holiday, I'll be allowed to
Mm.
stay with the drive for the whole of the next term.
Yes, but you don't access the classes we are holding during the term. You get the difference.
Meaning that
Yes,
you don't get access to the premium classes.
you don't. Because
Okay.
now we be handling home scholars.
Okay.
Yeah. So there is, I think
Thanks.
the screenshots are done. Yeah. The chapter 2, that one 9.2 is yours. For me, I'll come back to respond to the presentation and then we move to calorimetry. Okay, the last person is Innocent, then I leave this place. Yes, Innocent.
Good morning, Doctor and other guys. I am
Yes.
asking you,
Mm.
how do you have different drivers for candidates and S5Z?
Yes, they are
Oh,
different. They are different.
oh,
Though that of candidates is the one of candidates is having both senior 5 and 6. The one of senior 5 is having only senior 5, but it is the same work.
okay, I get you, Doctor.
Okay.
Have
So
a
you
blessed,
people,
have a blessed morning.
okay, okay. Okay, you people, I think
Thank you.
finally, bye. We are going to have further conversations, maybe from WhatsApp and from the WhatsApp groups. Otherwise,
Ate china
whatever I
inakumalia.
promised to send, you're supposed to
Amatude.
remind me. Whatever I've promised to send, you're supposed to remind me to send in case I forget. Otherwise, my last word is simple. Please make sure in whatever you're doing, you tell students about Science Scholars Academy. Whoever is benefiting from the classes, the best thing you can ever give back to SSA is telling more students about it. Yes, even when you leave senior 6, there are these young ones coming from senior 1. You just keep telling them. You tell those of senior 5 when you become a candidate. You also encourage them to tell others like that. So with awareness, those people will benefit. because time will reach maybe, and the free classes are too many for them. Okay, so you really need to do that. That's the best thing you can ever give back. Otherwise, thank you for is complying for the free classes and also coming through at the end. We shall keep doing this. If we do this for the whole year and we are consistent, trust me, we shall make it. If we shall have a full year of senior 6 revise. Remember, we have practicals to do, we have subsidiaries to handle. Even this content is supposed to be mastered. Yeah, I think that is it. And I can finally say bye, engineers. We shall meet next time, inshallah.